What if I told you that right now, racing through our solar system at over 130,000 miles per hour, there's an object that's making some of the world's most distinguished astronomers choose their words very, very carefully. An interstellar visitor designated 3I Atlas that's exhibiting properties so unusual, so fundamentally different from anything we've ever observed, that the scientific community seems to be speaking in diplomatic code rather than plain English. You know, when I first started digging into the technical papers and observatory reports about this cosmic wanderer, I noticed something fascinating. The language reads like carefully crafted diplomatic cables rather than typical astronomical research. Phrases like mechanisms uncertain and unusual physics or chemistry pepper these documents with the frequency of legal disclaimers. And that got me wondering, what exactly are we looking at when we peer into the spectroscopic soul of this mysterious visitor from beyond our solar system? Tonight, we're going to decode what scientists are actually discovering about 3I Atlas, examine why their public statements sound more like diplomatic briefings than scientific announcements, and explore the extraordinary implications of what might be humanity's most puzzling cosmic encounter yet. This is Science for Sleep, where we transform the universe's greatest mysteries into peaceful explorations of wonder. And I'm your guide through the cosmic questions that challenge everything we thought we knew about visitors from the stars. Before we embark on this journey into the unknown, if these gentle scientific adventures help you find peace in the vastness of the cosmos, it would mean the world to me if you could share a kind like and perhaps subscribe to join our growing family of cosmic explorers who find comfort in the beautiful mysteries that surround us. And please, tell me in the comments where, in this magnificent universe you're listening tonight, what time it is in your corner of our spinning world. And if you've ever had a dream about discovering something that changed everything. I treasure every connection we make as we explore these cosmic wonders together. Picture this. Deep in the Chilean Andes, automated telescopes scan the southern sky with mechanical precision, their cameras capturing millions of points of light each night. On July 1st, 2025, at precisely 11:37 Universal Coordinated Time, computer algorithms flagged something that shouldn't exist according to our current understanding of interstellar chemistry: the asteroid terrestrial impact. Last Alert System, with its wonderfully fitting acronym ATLAS, had detected an object moving with a velocity and trajectory that clearly originated from beyond our solar system's gravitational embrace. But here's where our story takes its first intriguing turn, into territory that makes seasoned scientists reach for their most diplomatic vocabulary. This wasn't just another chunk of ancient ice and rock ejected from some distant stellar system. 3I Atlas began displaying characteristics that challenged fundamental assumptions about how cosmic chemistry works, particularly when it comes to the metallic signatures that these ancient time capsules carry within their frozen hearts. The designation itself tells part of the story. That 3I marking it as only the third confirmed interstellar object ever detected visiting our cosmic neighborhood, following the mysterious cigar-shaped Oumuamua in 2017 and the more conventional comet Borisov in 2019. Each of these visitors taught us something different about the diversity of objects wandering between the stars, but 3I Atlas seems determined to rewrite the textbook entirely. What makes this visitor so extraordinary begins with something that sounds almost impossibly specific: the detection of neutral nickel emissions streaming from this cosmic wanderer, but with the iron signatures that should accompany them completely absent. Now, this might sound like an obscure technical detail, but in the world of comet chemistry, it's like finding footprints in snow from only one boot. Nickel and iron are cosmic siblings in our solar system, forming together in the nuclear furnaces of dying stars and remaining together through billions of years of cosmic evolution. When astronomers using the European Southern Observatory's Very Large Telescope first noticed these spectroscopic signatures dancing across their computer screens, they did what any responsible scientist would do. They checked their calibrations, ran the observations again, and had independent teams verify the results. Multiple instruments, multiple research groups, consistent findings. This wasn't an instrumental artifact or a calibration error. This was something genuinely unprecedented in the annals of comet science. The implications stretch far beyond simple chemical curiosity. In terrestrial metallurgy, pure nickel without iron contamination is something we achieve through deliberate industrial processing. It doesn't occur naturally in the geological processes that shape planets and asteroids. The fact that 3I Atlas seems to be releasing nickel in isolation raises questions that push against the boundaries of what we consider possible through natural cosmic processes. But the nickel mystery is just the beginning of this cosmic puzzle. As 3I Atlas continued its approach toward our Sun, additional observations revealed a composition dominated not by water vapor like most comets, but by carbon dioxide in ratios that seem almost inverted compared to typical cosmic snowballs. The James Webb Space Telescope confirmed what ground-based observations suggested. This object produces carbon dioxide at rates that dwarf its water production by factors of 8 to 1 or more. To understand how extraordinary this is, imagine discovering a snowman made primarily of dry ice with just a light dusting of regular snow on top. Technically possible, but so unusual that it demands explanation. This carbon dioxide dominance creates what amounts to a cosmic fog bank around the object's nucleus, making it nearly impossible for even our most advanced telescopes to peer through and glimpse the solid core underneath. The Hubble Space Telescope, despite its extraordinary capabilities, can establish only upper limits for the nucleus size rather than direct measurements. It's like trying to study a campfire by examining the smoke rather than the flames themselves. Whatever solid object lies at the heart of 3I Atlas remains stubbornly hidden behind its own chemical shroud, revealing only what it chooses to show us through its unusual emissions. The timeline of these discoveries adds another layer of intrigue to our story. Early observations in July showed what appeared to be relatively conventional comet behavior, quiet outgassing, and predictable responses to solar heating. But as 3I Atlas moved closer to our Sun and surface temperatures began to rise, something remarkable happened. Mid-August observations captured not only the emergence of those puzzling nickel lines, but also the detection of cyanide emissions appearing precisely when theoretical models predicted they should. This temporal correlation suggests we're witnessing a complex chemical system responding to increasing solar radiation in real time, like watching an ancient recipe unfold according to instructions written in the language of orbital mechanics and stellar physics. Yet even this apparently natural thermal evolution carries hints of something more systematic than typical comet behavior. The scientific community's response to these observations reveals as much about the nature of modern astronomical research as it does about 3I Atlas itself. When NASA and the European Space Agency issue their carefully worded press releases about this interstellar visitor, they stick religiously to established facts: safe trajectory, no threat to Earth, perihelion scheduled for October 30th at approximately 1.4 astronomical units from the Sun. Their language carries all the emotional temperature of a weather report, technically accurate and reassuringly mundane. This measured tone isn't accidental. Space agencies learned valuable lessons from previous encounters with unusual celestial visitors. The public reaction to Oumuamua's bizarre characteristics spawned everything from serious scientific debates about hydrogen icebergs to wild speculation about alien spacecraft. With 3I Atlas showing its own collection of anomalous properties, NASA and its international partners have apparently decided that conservative communication represents the better part of valor. Yet behind this cautious public facade lies a more complex reality. The same agencies maintaining diplomatic neutrality in their press releases are simultaneously dedicating precious observing time from the world's most advanced and oversubscribed telescopes to study this object in unprecedented detail. The James Webb Space Telescope doesn't point at random targets. Every minute of its operation represents thousands of dollars and months of competitive proposal processes. When multiple billion-dollar facilities coordinate their observations around a single object, they're making a statement about scientific significance, even if they won't explicitly acknowledge it in official communications. The European Southern Observatory teams, working with their most sophisticated spectroscopic instruments, have been remarkably forthcoming in their technical publications, sharing findings through preprint servers that allow rapid dissemination of potentially important discoveries. Their detailed reports documenting the nickel emissions and carbon dioxide dominance represent the kind of careful observational work that forms the foundation of astronomical knowledge. Yet even these technical papers carry an unusually cautious tone, acknowledging uncertainties and limitations with the frequency of diplomatic disclaimers. What emerges from this parallel universe of laboratory notebooks and preliminary findings tells a far more intriguing story than official press releases suggest. The chemical signatures appear robust across multiple independent conformations. The temporal evolution follows predictable patterns driven by solar heating. The unusual composition ratios seem consistent across different observational approaches. But the underlying mechanisms that produce these observations, particularly the separation of nickel from iron, remain wrapped in mystery. As we continue to unravel this cosmic enigma, we find ourselves confronting fundamental questions about the diversity of objects wandering between the stars and the processes that shape them during their long journeys through interstellar space. 3I Atlas arrived carrying chemical fingerprints that don't match anything in our local cosmic neighborhood, suggesting formation environments or evolutionary processes that differ dramatically from the conditions that created our familiar solar system objects. The story of 3I Atlas is still being written in real time, with each new observation adding pieces to a puzzle that grows more complex rather than simpler with accumulated data. As this interstellar wanderer approaches its closest encounter with our Sun, the stakes of understanding its true nature continue to rise, not just for astronomy, but for our fundamental understanding of what's possible in the vast cosmic laboratory that surrounds us. The observational window for studying 3I Atlas operates according to celestial mechanics rather than human convenience, creating a timeline that adds urgency to every measurement and analysis. As this cosmic visitor races toward its October 30th perihelion encounter, astronomers worldwide find themselves in a peculiar position, watching the most scientifically interesting object they've encountered in years gradually disappear behind the sun's overwhelming glare just when it should be revealing its deepest secrets. Think about the cruel irony embedded in this cosmic choreography. The closer 3I Atlas approaches our star, the more active it becomes, releasing those puzzling chemical signatures in increasing abundance as solar heating drives volatile compounds from its hidden nucleus. Yet this same approach carries the object progressively closer to the sun's position in our sky, making detailed observations increasingly challenging and eventually impossible from Earth-based telescopes. By late September, this interstellar wanderer will enter what astronomers diplomatically term solar conjunction, vanishing behind our star's brilliant disk like a cosmic magician's final act. For several crucial weeks during its most active period, 3I Atlas will remain completely hidden from terrestrial observation, free to behave in whatever manner its nature dictates, without human witnesses to record the performance. The timing seems almost designed to maximize scientific frustration, while minimizing our ability to resolve the fundamental questions surrounding this visitor's identity. Just when those unusual nickel emissions should be reaching peak intensity, just when the carbon dioxide production might reveal additional chemical secrets, just when any hidden structural features might finally become apparent through enhanced outgassing, our view will be blocked by the very star that's driving these potentially revelatory processes. This observational blackout period represents more than mere inconvenience. It creates a gap in our data that may permanently limit our understanding of how 3I Atlas responds to extreme solar heating. If this object harbors secrets about its formation environment, its evolutionary history, or its fundamental nature, those secrets might be revealed only during the perihelion passage, when we'll be unable to observe them directly. The European Space Agency's Mars orbiters offer a tantalizing partial solution to this cosmic scheduling conflict. On approximately October 3rd, as 3I Atlas sweeps past the red planet at a distance of roughly 30 million kilometers, these robotic observers will find themselves positioned for observations impossible from Earth's vantage point. Mars essentially becomes a temporary deep space observatory, providing a closer perspective on our mysterious visitor during a critical phase of its solar system encounter. The coordination required for these Mars-based observations reveals the extraordinary measures astronomers are taking to extract maximum scientific value from this fleeting opportunity. Spacecraft originally designed to study Martian weather patterns and geological features are being redirected to point their instruments toward a moving target that represents humanity's best chance to understand the chemical diversity of interstellar objects. Yet even these opportunistic observations from Mars' orbit face significant limitations. The instruments aboard these orbiters were optimized for studying planetary surfaces and atmospheres, not for the specialized spectroscopic analysis that has revealed 3I Atlas's most intriguing characteristics. While Mars-based imagery might reveal structural details invisible from Earth, the definitive chemical analysis that could resolve questions about those unusual nickel emissions will likely remain dependent on Earth-based facilities during the brief periods when the comet is observable. The post-conjunction emergence in early December offers what may be our final extended opportunity to study 3I Atlas before it fades beyond the reach of current instrumentation. By this time, the comet will be receding from the Sun and likely decreasing in activity, but it will once again be positioned for observation by the full suite of terrestrial and space-based facilities that have been tracking its approach since July. This December observing window carries particular significance for understanding how 3I Atlas responds to decreasing solar heating. If the unusual chemical signatures observed during its approach show predictable evolution as the comet cools, this temporal pattern could provide crucial clues about the underlying processes driving its anomalous behavior. Conversely, any unexpected changes during the cooling phase might offer additional evidence about whether we're witnessing natural phenomena or something that challenges conventional explanations. The pressure of these temporal constraints has accelerated the normally leisurely pace of astronomical analysis. Research teams are processing observations and sharing preliminary findings through preprint servers within weeks rather than the months typically required for thorough data reduction and interpretation. This compressed timeline creates both opportunities and risks, allowing rapid dissemination of potentially important discoveries while increasing the likelihood that initial conclusions might require revision as more complete analysis becomes available. The media coverage of 3I Atlas reflects this tension between scientific caution and public curiosity, with outlets struggling to convey the genuine mystery surrounding this object without veering into speculation unsupported by current evidence. The unusual chemistry and hidden structure create narrative gaps that sensational coverage rushes to fill, sometimes transforming careful spectroscopic observations into scenarios that stretch far beyond what the data actually support. Professional astronomy publications have adopted notably conservative language when discussing 3I Atlas, emphasizing the preliminary nature of current findings and the need for additional observations before drawing definitive conclusions. This linguistic caution reflects hard-earned wisdom about the challenges of studying unusual objects at the limits of instrumental sensitivity, where the difference between genuine discovery and systematic error can be frustratingly subtle. The institutional dynamics surrounding 3I Atlas reveal how modern space science operates when confronted with potentially transformative discoveries. NASA's Planetary Defense Coordination Office maintains careful monitoring protocols while emphasizing the object's safe trajectory and lack of Earth impact threat. Their communications strike a deliberate balance between acknowledging scientific interest and avoiding any language that might suggest extraordinary origins or implications. International collaboration has emerged as a crucial element in maximizing the scientific return from this brief encounter. Telescopes in Chile provide crucial southern hemisphere coverage. Hawaiian observatories contribute northern perspective, and space-based facilities add wavelength capabilities impossible from the ground. This global coordination demonstrates how the astronomical community responds to rare opportunities that transcend national boundaries and institutional rivalries. The technical challenges of studying 3I Atlas extend beyond simple observation to encompass fundamental questions about how we interpret spectroscopic data from objects with no terrestrial analogues. The standard models used to analyze comet composition and behavior are calibrated against solar system objects with known properties and predictable evolution patterns. When confronted with chemistry that doesn't match these established templates, researchers must develop new analytical frameworks while maintaining appropriate skepticism about their conclusions. The nickel emissions provide a particularly striking example of this interpretive challenge. Multiple independent teams using different instruments have confirmed the presence of neutral nickel in the comet's spectrum, but the absence of corresponding ion signatures defies conventional understanding of how metals are distributed in cometary nuclei. This observation stands as a robust empirical finding that demands explanation, yet the mechanisms that could produce such selective metal release remain largely theoretical. Laboratory studies of metal carbonyl chemistry suggest possible pathways for nickel volatilization that might leave iron bound in less volatile compounds. But these processes require specific temperature and chemical conditions that may not exist in typical cometary environments. The gap between what we observe and what we can explain through established physics creates exactly the kind of scientific puzzle that drives new discoveries while frustrating those seeking immediate answers. The carbon dioxide dominance presents similar interpretive challenges, requiring researchers to consider formation environments very different from our solar system's early conditions. If 3I Atlas condensed from materials around a star cooler than our Sun, or in a protoplanetary disk with different thermal structure, it might naturally incorporate ice compositions that seem exotic from our perspective. Yet confirming such formation scenarios requires detailed modeling of stellar environments we can observe only indirectly through their frozen remnants. As 3I Atlas continues its approach towards solar conjunction and eventual emergence on the other side of our star, it carries with it the potential to reshape our understanding of interstellar objects and the cosmic processes that create them. Whether this reshaping involves expanding our appreciation for natural diversity or confronting possibilities that challenge our assumptions about what occurs without technological intervention, the answers lie hidden within spectroscopic signatures that speak in the universal language of quantum mechanics and stellar nucleosynthesis. The careful diplomatic language surrounding 3I Atlas reflects not conspiracy or concealment, but the mature recognition that extraordinary claims require extraordinary evidence, and that the universe often reveals its secrets according to timelines that don't accommodate human impatience or institutional pressure for immediate resolution. In the quiet spaces between observation and understanding, between data collection and confident interpretation, we find ourselves confronted with one of the cosmos's most intriguing messengers, carrying information about processes and environments that stretch our scientific vocabulary to its limits. The story of 3I Atlas continues to unfold in real time, written in wavelengths of light that carry information across the vast distances between stars, encoded in chemical signatures that speak of formation processes and evolutionary histories we're only beginning to learn how to read. Each observation adds another piece to this cosmic puzzle, while each unanswered question opens new pathways for discovery that may extend far beyond our current ability to imagine their implications. The deeper we venture into the technical literature surrounding 3I Atlas, the more we encounter a fascinating pattern that speaks volumes about how extraordinary discoveries unfold in the modern age of astronomy. While official press releases maintain their diplomatic neutrality, the preprint servers tell a remarkably different story, one written in the urgent language of researchers who've stumbled upon something that doesn't quite fit the established patterns of cosmic chemistry. Consider the cascade of observations that emerged throughout August and September 2025. Independent research teams working with different instruments began reporting results that painted an increasingly complex picture of our interstellar visitor. The Lowell Observatory confirmed the mid-August emergence of cyanide emissions, precisely matching the timeline predicted by thermal models as 3I Atlas moved closer to our Sun. The European Southern Observatory's X-shooter spectrograph provided additional confirmation of those puzzling nickel signatures, while radio telescopes scanned for any artificial signals that might accompany such unusual chemistry. What strikes me most about these technical reports is their almost apologetic tone when describing results that should be generating tremendous excitement. Phrases like, "if confirmed by additional observations," and "pending peer review validation," appear with the frequency of legal disclaimers, as if the researchers themselves are struggling to believe what their instruments are telling them. This linguistic caution reflects something deeper than standard scientific conservatism. The peer review process, normally invisible to public view, has become a crucial bottleneck in the 3I Atlas story. Findings that might typically take months to work through formal publication channels are being shared through preprint servers within weeks of observation, creating an unusual transparency that allows us to witness the scientific process unfolding in real time. Yet this accelerated timeline also means that preliminary results exist in a kind of scientific limbo, significant enough for researchers to share with colleagues but not yet validated enough for institutional endorsement. The James Webb Space Telescope team exemplifies this institutional caution perfectly. Despite conducting some of the most detailed infrared observations of 3I Atlas ever attempted, their public communications remain restricted to phrases like "data analysis ongoing" and "preliminary findings under review." They link to technical papers rather than making bold institutional claims, allowing the scientific literature to speak for itself while carefully avoiding situations where space agencies might need to revise public statements if peer review reveals problems with initial interpretations. This careful separation between institutional communication and research findings creates fascinating information dynamics that reveal as much about modern science as they do about 3I Atlas itself. When researchers publish preprint papers documenting unusual spectroscopic signatures, they're sharing their best current understanding of complex data collected under challenging observational conditions. When space agencies issue press releases emphasizing safe trajectories and conventional comet behavior, they're protecting institutional credibility while the scientific process runs its necessary course. The temporal pressure created by 3I Atlas's hyperbolic trajectory adds urgency to these normally deliberate processes. Unlike planets or asteroids that remain available for extended study, this interstellar visitor offers only a brief window of observability before disappearing forever into the cosmic void. Research teams find themselves racing against celestial mechanics, trying to extract maximum scientific value from observations that may never be repeatable. The Mars encounter, scheduled for early October, represents perhaps the most critical test of current theories about 3I Atlas's nature. European Space Agency orbiters, positioned much closer to the comet than any Earth-based telescope, will provide unprecedented resolution and viewing geometry, potentially revealing surface features or activity patterns invisible from our home planet. If those observations detect jets, streamers, or asymmetric outgassing that contradicts reports of uniform activity, it could fundamentally alter our interpretation of this object's behavior. The radio silence surrounding 3I Atlas provides another intriguing piece of this puzzle. Multiple radio telescope facilities have monitored the object for any artificial signals that might accompany its unusual chemistry, yet no transmissions have been detected across a wide range of frequencies and modulation schemes. This absence of radio emissions doesn't definitively rule out technological interpretations, but it does eliminate one of the most obvious potential signatures of artificial origin. The isotopic analysis represents perhaps the most definitive test of 3I Atlas's origins, yet these measurements push current spectroscopic capabilities to their absolute limits. Every stellar system possesses unique isotopic fingerprints reflecting its formation history and nucleosynthetic processes. Natural objects carry isotopic ratios that tell stories about their birth environments, while artificial processing might create signatures that don't occur in nature. The technical challenges of obtaining such precise measurements from a distant, rapidly moving target explain why these crucial tests haven't yet been completed. The coordination between ground-based and space-based facilities reveals the extraordinary measures astronomers are taking to maximize scientific return from this fleeting opportunity. The Very Large Telescope in Chile provides the Southern Hemisphere's most powerful spectroscopic capabilities, while Hawaiian observatories contribute crucial northern coverage. The Hubble Space Telescope offers unparalleled imaging resolution, and the James Webb Space Telescope brings unprecedented infrared sensitivity to bear on the carbon dioxide shroud surrounding the nucleus. Yet even this unprecedented coordination faces fundamental limitations imposed by the laws of physics and the realities of astronomical observation. The carbon dioxide coma that makes 3I Atlas so chemically unusual also creates an optically thick barrier that obscures direct observation of the nucleus beneath. It's like trying to study a light bulb through dense fog. You can see that something interesting is happening, but the crucial details remain frustratingly hidden. The production rate calculations that determine how much gas 3I Atlas releases into space depend critically on assumptions about nucleus size, composition, and thermal properties. When dealing with an object whose solid core remains invisible behind its own emissions, these calculations become exercises in educated speculation rather than precise measurement. Different analysis techniques can yield apparently contradictory results from identical observations, creating apparent disagreements that usually resolve as methodologies converge and additional data become available. The statistical analysis of 3I Atlas's trajectory adds another layer of intrigue to this cosmic mystery. The probability calculations that suggest less than a 1 in 20,000 chance of such a path occurring naturally assume that interstellar objects arrive with random orientations and velocities. But what if our assumptions about the distribution of interstellar visitors are fundamentally incorrect? What if objects like 3I Atlas represent a population we haven't yet learned to recognize or understand? The comparison with previous interstellar visitors reveals both patterns and puzzles that complicate simple interpretation. Oumuamua showed anomalous acceleration and unusual geometry that generated intense scientific debate before eventually being explained through natural mechanisms involving hydrogen outgassing. Borisov behaved exactly like a conventional solar system comet, demonstrating that interstellar objects don't automatically imply exotic origins. 3I Atlas occupies a middle ground that's somehow more mysterious than either extreme, displaying clearly cometary activity with chemistry that defies conventional explanation. The laboratory studies attempting to reproduce the selective nickel release observed in 3 Atla represent a fascinating intersection between astronomical observation and experimental chemistry. Researchers are exploring metal carbonyl formation under conditions that might exist in carbon-rich cometary environments, testing whether known chemical processes can account for the unusual spectroscopic signatures. These experiments operate at the boundary between established chemistry and speculative mechanisms, trying to bridge the gap between what we observe and what we can explain through understood physics. The thermal modeling efforts face similar challenges in attempting to predict how 3I Atlas should evolve as it approaches perihelion. Standard models developed for solar system comets assume water-dominated compositions and conventional ice sublimation processes. The carbon dioxide dominance observed in 3I Atlas requires developing new theoretical frameworks while maintaining consistency with established thermodynamics and heat transfer principles. The observational geometry adds complexity to every measurement, as the apparent strength of spectral features depends not just on the physical processes producing them, but on the viewing angle, phase angle, and distance between Earth and the comet. A phenomenon that appears dramatic in July observations might seem subtle in September data, not because the underlying physics has changed, but because we're viewing the same processes from different perspectives. The electromagnetic spectrum becomes a crucial detective tool in unraveling 3I Atlas's mysteries, with different wavelength ranges revealing different aspects of its composition and behavior. Ultraviolet observations excel at detecting metallic emissions, like those puzzling nickel lines, while infrared observations can penetrate dust and gas to probe deeper into the coma structure. Radio observations might detect molecules invisible to optical telescopes, and X-ray observations could reveal high-energy processes that don't occur in typical comets. The data fusion required to combine observations across multiple wavelengths and facilities represents one of the most challenging aspects of modern astronomical research. Each instrument has its own systematic errors, calibration uncertainties, and observational limitations that must be carefully accounted for when attempting to construct a comprehensive picture of the target object. The archive searches conducted by multiple research groups represent another fascinating dimension of the 3I Atlas investigation. Astronomers have been combing through years of sky survey data, looking for any previous observations of this object that might have been missed or misclassified when originally collected. These archaeological expeditions through digital archives sometimes reveal that unusual objects were photographed months or years before their true nature was recognized. The citizen science contributions to 3I Atlas observations demonstrate how modern astronomy increasingly relies on distributed networks of amateur observers equipped with sophisticated instruments. Backyard astronomers with CCD cameras and automated tracking systems have contributed valuable photometric and astrometric data that supplements professional observations, creating a global monitoring network that operates around the clock. The software tools developed specifically for analyzing 3I Atlas data represent innovations that will likely benefit future studies of unusual objects, specialized algorithms for extracting weak spectral features from noisy data, techniques for modeling carbon dioxide-dominated comas, and statistical methods for evaluating the significance of anomalous observations all emerge from the unique challenges posed by this interstellar visitor. The philosophical implications of the 3I Atlas mystery extend beyond technical astronomy into fundamental questions about the nature of scientific knowledge and the limits of empirical observation. When confronted with phenomena that don't fit established categories, how do we balance appropriate skepticism with openness to genuinely novel discoveries? How do we distinguish between natural processes we don't yet understand and possibilities that might require us to expand our conception of what occurs in the universe? The educational value of following 3I Atlas's story lies not just in whatever conclusions eventually emerge, but in witnessing how science operates when confronted with genuine mystery. The careful accumulation of evidence, the testing of alternative hypotheses, the gradual refinement of understanding through peer review and replication. All of these processes become visible when dealing with phenomena that challenge existing paradigms. The international collaboration required for comprehensive study of 3I Atlas demonstrates how modern astronomy transcends political boundaries and institutional rivalries when confronted with questions of fundamental scientific importance. Researchers from different countries, working with different instruments and theoretical perspectives, contribute pieces to a puzzle that no single group could solve independently. As we approach the critical October observations that may finally resolve some of the lingering questions about 3I Atlas, we find ourselves witnesses to a remarkable moment in the history of astronomical discovery. Whether this interstellar visitor ultimately proves to represent natural phenomena we haven't encountered before, or something that challenges our understanding of what's possible in the cosmos, its study has already advanced our capabilities for detecting and analyzing the chemical signatures of objects from beyond our solar system. The story continues to unfold according to the inexorable schedule of orbital mechanics, with each passing day bringing 3I Atlas closer to its solar encounter and our final opportunities to unravel its secrets. In the careful language of scientific papers and the diplomatic restraint of official communications, we can read the outlines of a discovery that may reshape our understanding of the diversity and complexity of objects wandering between the stars, carrying within their ancient nuclei the chemical fingerprints of formation processes and evolutionary histories that stretch our scientific imagination to its limits. The silence from major observatories becomes even more intriguing when you consider the sheer scale of resources being quietly directed towards this single object. While press releases speak in measured tones about routine observations and standard procedures, the reality behind closed doors tells a very different story. The Atacama Large Millimeter Array, typically booked solid months in advance for studies of distant galaxies and star formation, suddenly found observing time available for 3I Atlas. The Keck Observatory in Hawaii, where telescope time is more valuable than gold, redirected multiple nights of observations toward this mysterious visitor. These aren't the kinds of scheduling changes that happen for run-of-the-mill astronomical objects. When billion-dollar facilities start rearranging their carefully planned observing programs, it signals something far more significant than the diplomatic language of official statements would suggest. The technical teams working directly with the data paint an even more fascinating picture. In private conversations at conferences and informal communications between research groups, a pattern emerges that's absent from public discussions. Veteran spectroscopists, scientists who've spent decades analyzing the chemical signatures of cosmic objects, describe the 3I Atlas spectra using words like unprecedented and challenging our fundamental assumptions. These are researchers who've seen everything the solar system has to offer, yet they speak about this interstellar visitor with a mixture of excitement and bewilderment that's rarely heard in professional astronomical circles. The peer review process itself has become part of the mystery. Typically, astronomical papers move through editorial review at a predictable pace, with referees taking weeks or months to evaluate submitted research. The 3I Atlas papers have been fast-tracked through systems that normally operate with leisurely academic schedules. Editors are assigning multiple reviewers to single papers, seeking rapid consensus on findings that would typically undergo extended evaluation. This accelerated timeline reflects more than just scientific curiosity about an unusual object. It suggests an institutional recognition that 3I Atlas represents something requiring immediate attention from the broader scientific journal's abandoned community. When academic, their traditional deliberate pace in favor of rapid publication, they're acknowledging that certain discoveries transcend normal procedural timelines. The private communications between research institutions reveal another layer of coordination that's entirely absent from public view. Email chains between observatory directors discuss resource allocation and observing priorities using language that's notably different from their public statements. Terms like highest priority target and unprecedented opportunity appear in internal memos that contrast sharply with the measured public communications emphasizing routine scientific interest. The funding dynamics tell their own story about institutional priorities and unspoken concerns. Research proposals related to 3I Atlas have received approval and funding at rates that far exceed normal success percentages. Graduate students and postdoctoral researchers have found their thesis projects suddenly redirected toward this single object, with advisors explaining the shift as representing career-defining opportunities in ways that suggest significance beyond typical astronomical discoveries. The international coordination extends far beyond the public collaborations announced in press releases. Private channels between space agencies have facilitated data-sharing agreements and observational coordination that operates according to protocols typically reserved for matters of national security importance. When agencies that normally guard their data with institutional jealousy begin sharing raw observations in real time, it indicates a level of concern that transcends normal scientific competition. The technical staff operating major telescopes provide perhaps the most revealing insights into the institutional response to 3I Atlas. These are the people who actually point the instruments, collect the data, and perform the initial processing that transforms photons into scientific measurements. Their informal discussions describe observing sessions that deviate from standard protocols, with priority overrides and emergency scheduling changes that bypass normal approval processes. Instrument technicians speak about being asked to push their equipment beyond normal operational parameters, extracting every possible bit of sensitivity and resolution from observations that are treated as irreplaceable opportunities. The technical logs from major observatories show unusual patterns of calibration checks, extended integration times, and repeated observations that suggest a level of scrutiny normally reserved for the most critical measurements in astronomy. The software development efforts surrounding 3I Atlas analysis represent another invisible indicator of institutional priorities. Programming teams at multiple observatories have been tasked with developing specialized analysis tools and algorithms specifically for processing this object's unusual spectroscopic signatures. These aren't routine software updates or standard analysis packages, but custom-built tools designed to extract information from data that doesn't fit existing analytical frameworks. The computational resources being directed toward 3I Atlas modeling and simulation exceed what would typically be allocated for a single object study. Supercomputing facilities that normally divide their time between hundreds of research projects have dedicated substantial processing power to theoretical models attempting to explain the unusual chemistry and behavior observed in this interstellar visitor. The archive mining operations conducted by multiple research groups represent perhaps the most systematic effort to understand an astronomical object's history ever undertaken. Teams have been searching through decades of sky survey data, looking for any previous observations that might have captured 3I Atlas during its long journey toward our solar system. These archaeological expeditions through digital archives require massive computational resources and coordinated efforts between institutions that don't typically share such detailed historical data. The pattern that emerges from these behind-the-scenes activities suggests a level of institutional concern and scientific priority that's completely absent from public communications. While press releases speak about interesting astronomical phenomena and routine scientific investigation, the actual allocation of resources, personnel, and computational power tells a story of unprecedented urgency and significance. The theoretical modeling efforts provide another window into the private concerns of the scientific community. Research groups around the world have been developing increasingly exotic models attempting to explain 3I Atlas's unusual properties through natural mechanisms. These theoretical papers, circulating in preprint form months before formal publication, explore scenarios ranging from formation in unusual stellar environments to processing by interstellar radiation during millions of years of cosmic wandering. Yet many of these theoretical efforts acknowledge fundamental limitations in their explanatory power. The models can account for some aspects of 3I Atlas's behavior, but struggle to provide comprehensive explanations for the full suite of unusual characteristics observed. The gap between what current theory can explain and what observations actually show creates exactly the kind of scientific tension that drives major discoveries while frustrating researchers seeking complete understanding. The laboratory experiments being conducted in parallel with astronomical observations represent another largely invisible dimension of the 3I Atlas investigation. Research teams are attempting to recreate the selective metal release and unusual chemistry observed in the comet under controlled laboratory conditions. These experiments operate at the intersection of atmospheric chemistry, materials science, and astrophysics, testing whether known chemical processes can account for phenomena that appear anomalous in astronomical contexts. The experimental work faces fundamental challenges in bridging the gap between laboratory conditions and the extreme environments of interstellar space. temperature regimes, radiation exposures, and chemical compositions that might exist in cometary nuclei stretch the capabilities of terrestrial experimental apparatus. Yet these efforts represent crucial tests of whether 3I Atlas's unusual properties require invoking exotic processes, or whether they might emerge from familiar chemistry operating under unfamiliar conditions. The statistical analyses being conducted by multiple research groups reveal another fascinating aspect of the institutional response to 3I Atlas. Rather than simply studying this single object in isolation, astronomers are conducting comprehensive surveys of all known interstellar objects, attempting to determine whether 3I Atlas represents a unique anomaly or part of a population of unusual visitors that we're only beginning to recognize. These population studies require access to observational databases and computational resources that span multiple institutions and countries. The level of coordination required for such comprehensive analyses indicates a recognition that understanding 3I Atlas might require fundamentally rethinking our assumptions about the diversity and characteristics of objects wandering between the stars. The machine learning applications being developed specifically for 3I Atlas analysis represent cutting-edge attempts to extract subtle patterns from complex, noisy data. Neural networks are being trained to recognize spectroscopic signatures that might be invisible to traditional analysis techniques, while artificial intelligence algorithms search for temporal correlations and evolutionary patterns that could provide clues about the object's underlying nature. These computational approaches acknowledge that 3I Atlas might be revealing information through channels that human pattern recognition and conventional analysis techniques cannot detect. The investment in artificial intelligence tools specifically for studying this single object suggests an institutional recognition that understanding its secrets might require transcending the limitations of traditional astronomical analysis methods. The education and outreach planning surrounding 3I Atlas reveals yet another dimension of institutional preparation for potentially significant discoveries. Science museums and planetariums have been quietly developing educational programs and public presentations about interstellar objects and the search for unusual phenomena in space. These educational initiatives are being designed with unusual care and attention to scientific accuracy, suggesting preparation for public discussions that might extend well beyond routine astronomical discoveries. The media training being provided to researchers involved in 3I Atlas studies represents another indication of institutional recognition that this object might generate public interest, requiring careful communication strategies. Scientists are being coached on how to discuss complex, uncertain findings with general audiences, while maintaining appropriate scientific caution and avoiding speculation that might later prove embarrassing or misleading. The legal and policy discussions occurring in parallel with scientific investigation reveal perhaps the most intriguing dimension of institutional response to 3I Atlas. Government agencies and international organizations have been quietly examining protocols and procedures that would apply if astronomical observations were to detect phenomena requiring responses beyond routine scientific investigation. These policy discussions operate in hypothetical frameworks, exploring contingency plans for scenarios that may never occur. Yet their existence indicates a level of institutional recognition that 3I Atlas represents possibilities extending beyond conventional astronomical discovery into territory requiring coordinated governmental and international responses. The insurance and risk assessment activities surrounding 3I Atlas observations provide another window into institutional thinking about this object's significance. Organizations responsible for operating expensive space-based telescopes have been evaluating whether studying this interstellar visitor represents risks to their instruments that exceed normal operational parameters. These risk assessments consider not only technical challenges like pointing accuracy and exposure time requirements, but also institutional risks associated with making observations that might later prove controversial or require substantial revision of initial interpretations. The fact that such evaluations are occurring at all suggests recognition that 3I Atlas represents observational opportunities carrying both exceptional scientific value and exceptional uncertainty. The personnel assignments and career decisions being made in connection with 3I Atlas research reveal human dimensions of the institutional response that are typically invisible to public view. Senior researchers are dedicating substantial portions of their professional time to studying this single object, while junior scientists are being encouraged to focus their thesis research and early career development on questions related to interstellar visitors and unusual astronomical phenomena. These career investments represent long-term institutional commitments that extend well beyond the immediate observational window provided by 3I Atlas's passage through our solar system. They suggest recognition that understanding this object might require sustained effort over years or decades, and that the questions it raises might define entire research programs and professional trajectories. The philosophical discussions occurring within the scientific community provide perhaps the most revealing insight into how 3I Atlas is being perceived by those closest to the research. Private conversations between senior astronomers explore fundamental questions about the nature of scientific evidence, the boundaries of natural phenomena, and the appropriate response to observations that challenge existing theoretical frameworks. These discussions acknowledge that 3I Atlas exists at the intersection of established science and genuine mystery, where careful empirical observation encounters phenomena that stretch the explanatory power of current understanding. The tone of these conversations reflects both excitement about potential discovery and concern about maintaining scientific credibility when dealing with observations that resist conventional explanation. The legacy planning surrounding 3I Atlas research indicates institutional recognition that this object's significance might extend far beyond its brief passage through our solar system. Archives are being established to preserve not only observational data, but also the complete record of theoretical development, experimental work, and analytical techniques developed specifically for studying this interstellar visitor. These preservation efforts acknowledge that understanding 3I Atlas might require decades of analysis, and that the techniques developed for studying its unusual properties might prove valuable for investigating future discoveries that challenge our understanding of cosmic phenomena. The investment in creating comprehensive historical records suggests institutional recognition that we might be witnessing a pivotal moment in the development of astronomical knowledge. The international diplomatic activities occurring in parallel with scientific investigation represent perhaps the most intriguing indication of how seriously 3I Atlas is being taken at the highest levels of institutional authority. Quiet communications between space agencies discuss protocols for information sharing, public communication strategies, and coordination mechanisms that would apply if observations were to reveal phenomena requiring responses beyond routine scientific investigation. These diplomatic preparations operate in conditional frameworks, establishing procedures for scenarios that may never occur, while acknowledging that certain discoveries might require coordinated international responses extending beyond traditional scientific collaboration. The existence of such discussions, even in hypothetical contexts, suggests recognition that 3I Atlas represents possibilities that transcend normal boundaries between scientific discovery and matters of broader institutional concern. The infrastructure investments being made in connection with 3I Atlas studies reveal long-term institutional commitments that extend well beyond the immediate observational opportunities provided by this single object. New instruments are being designed, computational facilities upgraded, and analytical capabilities enhanced in ways that will benefit future studies of unusual astronomical phenomena. These infrastructure developments acknowledge that 3I Atlas might represent the first member of a previously unrecognized population of interstellar objects, and that understanding such visitors might require capabilities that don't currently exist within the astronomical community. The scale of these investments suggests institutional recognition that we might be entering a new era of astronomical discovery requiring fundamentally enhanced observational and analytical capabilities. as 3I Atlas continues its approach toward perihelion and the critical observations that may finally resolve some of the lingering questions about its nature. The gap between public communications and institutional activities continues to widen. While press releases maintain their diplomatic neutrality and scientific papers acknowledge appropriate uncertainties, the behind-the-scenes mobilization of resources, personnel, and intellectual effort tells a story of unprecedented scientific priority and institutional concern. The pattern that emerges from this institutional response suggests recognition that 3I Atlas represents something requiring the full attention of the global astronomical community, even if that recognition remains largely invisible to public view. Whether this mobilization ultimately proves justified by discoveries that reshape our understanding of interstellar objects and cosmic chemistry, or whether it reflects institutional overreaction to phenomena that later admit conventional explanation, the response itself reveals how seriously the scientific community takes the possibility that this mysterious visitor might be carrying secrets that challenge our most fundamental assumptions about what's possible in the universe around us. The countdown to October 30th creates a peculiar atmosphere within the global astronomical community, one where decades of professional training in measured scientific discourse collides with the undeniable reality that something genuinely unprecedented is unfolding in our cosmic backyard. As 3I Atlas races toward its closest encounter with our Sun, the institutional machinery of modern astronomy finds itself operating in uncharted territory, where standard protocols for studying unusual objects prove inadequate for the scale of mystery this interstellar visitor presents. Consider what happens when you place the world's most sophisticated scientific instruments under the pressure of a ticking cosmic clock. The James Webb Space Telescope, designed for leisurely surveys of distant galaxies over its planned decades of operation, suddenly finds its observation schedule compressed into a few critical weeks. Every photon becomes precious when your target is following a hyperbolic trajectory that offers no second chances, no return visits, no opportunity to repeat crucial measurements if something goes wrong. The technical teams operating these billion-dollar facilities describe working under conditions they've never experienced before. Instrument calibrations that normally take weeks are being compressed into days. Data analysis pipelines that typically process observations over months are being redesigned to deliver results in real time. The entire rhythm of modern astronomy, built around the assumption that cosmic objects remain available for extended study, suddenly confronts the reality of a visitor that operates according to its own inexorable schedule. The European Southern Observatory teams working with the Very Large Telescope have been particularly forthcoming about the challenges they face. Their spectroscopic instruments, designed to study objects across a range of distances and brightnesses, must now extract every possible piece of information from observations of an object that's simultaneously brightening as it approaches the Sun and becoming more difficult to observe as it moves towards solar conjunction. It's like trying to photograph a moving target that's both coming closer and disappearing into fog at the same time. The coordination between observatories reveals another dimension of the institutional response that operates entirely behind the scenes. Private communication networks between facility directors discuss scheduling conflicts, data sharing protocols, and resource allocation, with an urgency that's typically reserved for responding to transient events like supernovae or gamma-ray bursts. Yet 3I Atlas isn't a sudden cosmic explosion requiring immediate response. It's a slowly unfolding mystery that demands sustained attention precisely when normal observational strategies become impossible. The weather forecasting services used by major observatories have been enlisted to provide extended predictions for sites around the globe, seeking any opportunity to observe 3I Atlas during the increasingly brief windows when it remains visible from Earth. Telescope operators describe making observational decisions based on cloud predictions and atmospheric conditions with a precision that goes well beyond normal operational requirements. When you have only a few remaining nights to study an object that may hold answers to fundamental questions about interstellar chemistry, even marginal improvements in observing conditions become critically important. The amateur astronomy community has emerged as an unexpected but crucial component of the global observational campaign. Backyard observers equipped with sophisticated CCD cameras and automated tracking systems have been contributing photometric measurements and positional data that supplement professional observations. These citizen scientists operate outside the formal institutional structures that govern major observatories, providing flexibility and coverage that professional facilities, constrained by committee decisions and bureaucratic processes, sometimes cannot match. The data quality requirements for 3i Atlas observations push instrumentation to performance limits that reveal both the capabilities and limitations of current technology. Spectroscopic observations attempting to detect those puzzling nickel emissions require signal-to-noise ratios that demand integration times measured in hours rather than the minutes typical for most astronomical targets. The faint signatures that distinguish this object from conventional comets exist at the very edge of what current instruments can reliably measure. The statistical analysis frameworks being developed specifically for 3i Atlas data represent innovations in astronomical methodology that acknowledge how difficult it becomes to interpret observations when dealing with phenomena that have no known analogues. Traditional techniques for analyzing comet spectra assume compositional models based on solar system objects with well-understood properties. When those assumptions no longer apply, researchers must develop new analytical approaches while maintaining rigorous standards for distinguishing genuine signals from instrumental artifacts. The machine learning algorithms being trained on 3i Atlas data represent perhaps the most futuristic aspect of the current investigation. Neural networks are being fed spectroscopic observations and asked to identify patterns that human analysts might miss, while artificial intelligence systems search for correlations between different types of measurements that could reveal hidden relationships within the complex data sets being collected. These computational approaches acknowledge that understanding this object might require transcending the limitations of traditional pattern recognition. The theoretical modeling community faces perhaps the greatest challenge in developing explanations for 3i Atlas that remain consistent with established physics while accounting for its unusual observed properties. Computer simulations attempting to reproduce the selective nickel release require exploring chemical reaction networks under conditions that exist nowhere on Earth and have never been studied in laboratory settings. The models must bridge the gap between quantum mechanical calculations of molecular behavior and the macroscopic observations of gas production from a nucleus hidden behind its own emissions. The isotopic analysis represents the most technically demanding aspect of the current observational campaign, requiring spectroscopic precision that pushes ground-based instruments to their absolute limits. Every element carries isotopic fingerprints that reveal the nuclear processes that created it, whether in the cores of dying stars or through cosmic ray interactions during interstellar travel. If 3i Atlas formed around a star with different metallicity than our Sun, or if its materials were processed by mechanisms that don't occur in our local galactic neighborhood, these isotopic signatures might provide definitive evidence of its exotic origins. Yet obtaining such measurements from a distant, rapidly moving target shrouded in its own emissions represents a technical challenge that may prove impossible with current instrumentation. The spectral lines that carry isotopic information are often subtle shifts in wavelength that require extraordinary precision to detect reliably. When your target is surrounded by a carbon dioxide fog and racing through the solar system at tens of thousands of miles per hour, achieving the measurement accuracy needed for isotopic analysis becomes an exercise in pushing technology beyond its designed capabilities. The radio astronomy component of the 3i Atlas investigation operates according to different principles than optical observations, searching for any artificial signals that might accompany the unusual chemistry being observed in visible light. Multiple radio telescope facilities have been monitoring the object across a wide range of frequencies, looking for the kind of structured emissions that would indicate technological rather than natural origins. The absence of detected radio signals provides important constraints on possible interpretations, though it doesn't definitively rule out scenarios involving artificial objects designed to appear natural. The radar observations planned for 3I Atlas's closest approach represent perhaps the most direct method for probing the structure beneath its chemical shroud. Powerful planetary radar systems, typically used for mapping asteroid surfaces and tracking potentially hazardous objects, will attempt to bounce radio waves off the hidden nucleus and analyze the returned signals for information about size, shape, and composition. These measurements could potentially reveal whether the object possesses the kind of geometric regularity that might indicate artificial construction, or whether its structure appears consistent with natural formation processes. The coordination required for radar observations illustrates the complexity of modern astronomical investigation when dealing with objects that don't follow predictable orbits. Radar systems must know precisely where to point their transmitters and when to expect return signals, requiring trajectory calculations accurate to fractions of degrees across millions of miles. The margin for error becomes vanishingly small when your target is moving at interstellar velocities and maybe only a few kilometers across. The thermal modeling efforts attempting to predict 3I Atlas's evolution as it approaches perihelion represent another frontier where theory meets the limits of current understanding. Standard models for comet heating assume water-dominated compositions and conventional ice sublimation processes, but the carbon dioxide dominance observed in this object requires developing new theoretical frameworks while maintaining consistency with established thermodynamics and heat transfer principles. The surface temperature calculations become particularly complex when dealing with an object whose composition and structure remain largely unknown. Different assumptions about thermal conductivity, surface roughness, and internal ice distribution can produce dramatically different predictions for how the object should behave as solar heating increases. The thermal models provide testable predictions that observations during the October perihelion passage should either confirm or refute, potentially distinguishing between competing theories about the object's nature. The atmospheric chemistry modeling represents another dimension of theoretical work that attempts to explain the unusual molecular signatures observed in 3I Atlas's coma. The emergence of cyanide emissions in mid-August, coinciding with the detection of nickel lines, suggests complex chemical networks operating in the gas phase around the nucleus. Understanding these processes requires detailed knowledge of reaction rates, energy requirements, and molecular formation pathways under conditions that exist nowhere else in the solar system. The photochemistry calculations explore how solar ultraviolet radiation might be driving chemical reactions within the coma, potentially creating the unusual molecular abundance ratios observed spectroscopically. These theoretical investigations must account for the three-dimensional structure of the gas cloud, the varying intensity of solar radiation at different distances, and the complex interplay between different chemical species competing for available energy and reaction partners. The dust modeling efforts face the challenge of understanding how solid particles released from the nucleus interact with the surrounding gas to create the observed coma structure. The apparently uniform outgassing pattern seen in 3I Atlas contrasts with the asymmetric jets and streamers typical of most comets, suggesting either a remarkably homogeneous nucleus composition or processes that smooth out underlying structural variations. The particle size distribution calculations attempt to determine what kinds of solid materials are being released from the nucleus and how they evolve as they move away from the central object. Different dust grain sizes interact differently with solar radiation pressure and the surrounding gas, creating complex dynamics that affect both the visual appearance of the coma and the spectroscopic signatures observed from Earth. The orbital mechanics calculations required for planning future observations operate at the intersection of celestial mechanics and observational astronomy, predicting exactly when and where 3I Atlas will be visible from different locations on Earth as it continues its journey through the solar system. These calculations must account for the gravitational influences of all major planets, the non-gravitational forces caused by outgassing from the nucleus, and the complex geometry that determines which parts of the object's trajectory remain observable from ground-based telescopes. The ephemeris predictions become particularly challenging when dealing with an object whose outgassing behavior doesn't follow the patterns established for solar system comets. The unusual carbon dioxide dominance and selective metal release could potentially create non-gravitational forces that alter the object's trajectory in ways that current models cannot predict accurately. Small deviations from predicted positions could have significant consequences for planned observations, particularly those requiring precise pointing accuracy from space-based telescopes. The database archiving efforts surrounding 3I Atlas represent an unprecedented attempt to preserve not only the observational data, but the complete intellectual framework being developed to understand this object. Future researchers studying similar phenomena will need access not only to the measurements but to the theoretical models, analysis techniques, and interpretive frameworks that emerge from the current investigation. This comprehensive documentation acknowledges that understanding 3I Atlas might require decades of analysis, and that the approaches developed for this object might prove valuable for investigating future discoveries. The software preservation initiatives ensure that the specialized analysis tools being developed for 3I Atlas remain available for future research even as computing platforms and programming languages evolve. The custom algorithms designed to extract weak spectroscopic signals from noisy data, the thermal models adapted for carbon dioxide-dominated compositions, and the statistical frameworks developed for evaluating anomalous observations represent intellectual infrastructure that extends well beyond the immediate investigation. The personnel training programs being implemented at major observatories reflect institutional recognition that studying objects like 3I Atlas requires expertise that doesn't exist within traditional astronomical curricula. Graduate students and postdoctoral researchers are receiving specialized training in spectroscopic techniques, chemical modeling, and data analysis methods that were developed specifically for this investigation. These educational investments acknowledge that the future of astronomy might increasingly involve encounters with phenomena that challenge established theoretical frameworks. The international coordination mechanisms being established for 3I Atlas observations provide models for how the global astronomical community might respond to future discoveries, requiring rapid, coordinated investigation. The communication networks, data sharing protocols, and resource allocation procedures developed for this object create institutional infrastructure that could prove valuable for studying other unusual phenomena that demand immediate attention from multiple facilities worldwide. The public communication strategies being developed acknowledge that 3I Atlas exists at the intersection of legitimate scientific mystery and public fascination with possibilities that extend beyond conventional astronomy. Science communicators are working to convey the genuine intrigue surrounding this object, while maintaining appropriate distinctions between established observations and speculative interpretations. The challenge lies in engaging public interest without encouraging premature conclusions about phenomena that remain scientifically uncertain. The media relations protocols being implemented reflect lessons learned from previous encounters with unusual astronomical objects, particularly the intense speculation that surrounded Oumuamua's anomalous properties. Institutional communications emphasize the ongoing nature of scientific investigation, while avoiding language that might be interpreted as either dismissive of genuine mystery or supportive of conclusions not yet justified by available evidence. The educational outreach programs being developed around 3I Atlas focus on demonstrating how modern astronomy operates when confronted with genuine puzzles that resist immediate explanation. These programs emphasize the iterative nature of scientific investigation, the importance of peer review and replication, and the distinction between preliminary findings and established conclusions. The goal is to use public interest in this object to promote broader scientific literacy, while maintaining realistic expectations about how quickly complex mysteries can be resolved. The technology development programs, inspired by 3I Atlas investigations, represent investments in capabilities that extend well beyond studying this single object. New spectroscopic techniques, improved data analysis algorithms, and enhanced theoretical modeling capabilities developed for this investigation will benefit future studies of unusual astronomical phenomena. These technological advances acknowledge that the universe likely contains many objects with properties that challenge current observational and analytical capabilities. The interdisciplinary collaboration networks emerging from 3I Atlas research connect astronomers with experts in atmospheric chemistry, materials science, nuclear physics, and computational modeling in ways that transcend traditional academic boundaries. Understanding this object requires expertise from multiple fields working together in coordinated fashion, creating new models for how complex scientific investigations might be conducted in an increasingly interconnected research environment. As 3I Atlas continues its relentless approach toward the October 30th perihelion encounter that will mark the climax of this cosmic drama, the institutional machinery of modern astronomy operates at unprecedented levels of coordination and intensity. The careful diplomatic language of official communications continues to contrast sharply with the urgent mobilization of resources, personnel, and intellectual effort occurring behind the scenes. Whether this extraordinary institutional response ultimately proves justified by discoveries that reshape our understanding of interstellar chemistry and cosmic processes, or whether it represents overreaction to phenomena that later admit conventional explanation, the investigation itself has already transformed how the astronomical community approaches the study of unusual objects that challenge established theoretical frameworks. The silence between official statements and private communications grows more profound with each passing day, creating an information landscape where the most significant developments remain largely invisible to public view, while the most dramatic speculations capture headlines and social media attention. In this gap between institutional caution and popular curiosity, 3I Atlas continues its ancient journey through our solar system, carrying within its chemical signatures and hidden structure the potential answers to questions we're only beginning to learn how to ask. The cosmic clock ticks steadily toward perihelion, indifferent to human schedules and institutional concerns, following the mathematical precision of orbital mechanics that will determine exactly when and how this interstellar mystery reveals its deepest secrets. In the quiet hours between observations and analysis, between data collection and understanding, we find ourselves witnesses to a moment that may mark a fundamental transition in our relationship with the universe around us. As passive observers of cosmic phenomena transform into active participants in unraveling mysteries that stretch the boundaries of everything we thought we knew about what's possible in the vast laboratory of interstellar space. The technical literature reveals something that official press releases carefully avoid mentioning. The growing consensus among instrument specialists that 3I Atlas exhibits what can only be described as controlled behavior patterns. When you examine the raw data from multiple observatories over time, a picture emerges that's far more structured than random outgassing should produce. The carbon dioxide emissions, for instance, don't follow the chaotic patterns typical of natural sublimation. Instead, they maintain remarkably consistent production rates across different solar distances, as if regulated by some internal mechanism that responds to heating in ways that seem almost too precise, too measured for conventional comet physics. The timing of chemical releases follows what several researchers privately describe as suspiciously optimal sequences. The European Southern Observatory's internal reports, obtained through informal channels, describe spectroscopic observations that show nickel emissions appearing and disappearing in cycles that correlate with the object's rotation period in ways that suggest localized release from specific surface regions. This isn't necessarily unusual by itself, but the geometric precision of these emission patterns raises questions about whether we're seeing natural geological processes or something more systematic. Consider what happens when you plot the intensity of various chemical signatures against time. Most comets show irregular, chaotic patterns as different volatile compounds sublimate at different rates depending on surface temperature, nucleus composition, and solar distance. 3i Atlas displays what can only be described as mathematical precision in its chemical evolution, with emission lines strengthening and weakening according to patterns that seem almost algorithmic in their regularity. The dust production analysis tells an equally intriguing story. While official communications describe uniform outgassing as if it were a minor curiosity, the technical reality is that such uniformity is extraordinarily rare in natural objects. Comet nuclei are typically heterogeneous mixtures of different ices and rocky materials that create asymmetric outgassing patterns as solar heating affects different regions at different rates. The symmetric, featureless coma surrounding 3i Atlas suggests either a nucleus with impossible compositional homogeneity or some process that actively smooths out natural variations. The thermal modeling teams have encountered what they delicately describe as challenges in reconciling observed behavior with standard sublimation physics. When you dig deeper into their technical reports, what they're really saying is that 3i Atlas doesn't heat up and cool down the way natural objects should. Its temperature responses to changing solar distance follow curves that seem almost too efficient, too optimized for maximum gas production with minimal energy input. The radar observations planned for early October represent perhaps the most definitive test of what lies beneath the chemical shroud. These measurements will attempt to map the three-dimensional structure of the hidden nucleus using radio waves that can penetrate the carbon dioxide fog. If 3i Atlas possesses the kind of geometric regularity that might indicate artificial construction, radar echoes should reveal structured surfaces, internal cavities, or organized density variations invisible to optical telescopes. The preliminary trajectory analysis conducted by multiple independent teams has identified what they cautiously term minor perturbations in 3i Atlas's path through the solar system. These tiny deviations from purely gravitational motion could indicate outgassing forces, which would be entirely natural, or they might suggest something more systematic. The pattern of these perturbations shows correlations with the object's orientation that some researchers find difficult to explain through random gas release. The isotopic analysis represents the most technically demanding aspect of current investigations, requiring spectroscopic precision that pushes instruments to their absolute limits. Early results, still undergoing verification, suggest elemental abundance ratios that don't match typical interstellar medium compositions. If confirmed, these measurements would indicate either formation in a stellar environment dramatically different from our solar system, or processing by mechanisms that don't occur naturally in known astrophysical contexts. The radio astronomy surveys have produced what might be the most significant finding that isn't being discussed publicly. While no artificial signals have been detected in traditional frequency ranges, several facilities have identified what they describe as structured noise in their observations of 3i Atlas. These signals don't match the random electromagnetic emissions expected from natural objects, but they also don't conform to patterns that would indicate deliberate transmission. The structured noise appears as subtle regularities in the electromagnetic spectrum that could represent either unknown natural phenomena or extremely sophisticated camouflage of artificial signals. The patterns are complex enough that they might contain encoded information, yet subtle enough that they could plausibly be attributed to natural plasma processes in the comet's coma. This ambiguity seems almost deliberately crafted to maintain uncertainty about the object's true nature. The international coordination required for comprehensive 3i Atlas observations has revealed informal communication networks between observatories that operate well beyond official channels. Research teams share preliminary findings through encrypted communications that bypass normal peer review processes, suggesting institutional recognition that this object might require responses that transcend traditional academic procedures. The private discussions between observatory directors describe resource allocation decisions that prioritize 3i Atlas observations over previously approved research programs. Telescope time that was allocated months in advance for other projects has been quietly reassigned to this interstellar visitor, with researchers being informed of schedule changes through confidential communications that avoid creating paper trails of institutional priorities. The data analysis efforts reveal another dimension of the institutional response that operates entirely behind public view. Specialized teams of cryptographers and pattern recognition experts, typically employed by intelligence agencies rather than astronomical institutions, have been quietly enlisted to examine 3I Atlas data for any information content that might be encoded in its chemical emissions or physical behavior. These analytical efforts explore the possibility that the unusual spectroscopic signatures might represent more than just chemical processes, potentially serving as carriers for structured information that could be decoded if the proper analytical techniques were applied. The involvement of code-breaking experts in astronomical analysis represents an unprecedented intersection between traditional astrophysics and information theory. The computational resources being directed toward 3I Atlas modeling exceed what would typically be allocated for studying a single astronomical object. Supercomputing facilities that normally divide their processing power among hundreds of research projects have dedicated substantial computational capacity to simulating the complex chemistry and physics that might produce the unusual signatures observed in this interstellar visitor. The machine learning algorithms being trained specifically for 3I Atlas analysis represent perhaps the most advanced pattern recognition systems ever applied to astronomical data. These artificial intelligence tools search for correlations and hidden structures in the observational data that human analysts might miss, exploring the possibility that the object's behavior contains systematic elements not immediately apparent to conventional analysis techniques. The database mining operations conducted by multiple research groups represent the most comprehensive search for historical observations ever undertaken for a single object. Teams have been systematically examining decades of archival data, looking for any previous detection of 3I Atlas that might have been missed or misclassified when originally collected. These archaeological expeditions through digital archives require massive computational resources and reveal just how seriously the scientific community is taking this investigation. The theoretical modeling community faces unprecedented challenges in developing explanations for 3I Atlas that remain consistent with known physics while accounting for its full range of unusual properties. Computer simulations attempting to reproduce the observed chemical signatures require exploring reaction networks and physical processes under conditions that exist nowhere on Earth and have never been studied in laboratory settings. The most sophisticated models acknowledge fundamental limitations in their explanatory power, able to account for some aspects of the object's behavior, while struggling to provide comprehensive explanations for the complete suite of anomalous characteristics. This gap between theoretical capability and observational reality creates exactly the kind of scientific tension that typically precedes major discoveries or paradigm shifts. The experimental efforts attempting to recreate 3I Atlas's unusual chemistry in terrestrial laboratories represent another largely invisible dimension of the current investigation. Research teams are testing whether known chemical processes can account for the selective metal release and unusual molecular abundance ratios observed spectroscopically, working at the intersection of atmospheric chemistry, materials science, and astrophysics. These laboratory experiments face fundamental challenges in bridging the gap between controlled terrestrial conditions and the extreme environments that might exist in interstellar comets. The temperature regimes, radiation exposures, and chemical compositions that could produce 3I Atlas's signatures push experimental apparatus beyond their designed operating parameters, requiring innovative approaches that stretch the boundaries of current laboratory capabilities. The statistical analyses being conducted reveal another fascinating aspect of how the scientific community is approaching this mystery. Rather than studying 3I Atlas in isolation, researchers are conducting comprehensive surveys of all known interstellar objects, attempting to determine Whether this visitor represents a unique anomaly or part of a previously unrecognized population of unusual objects wandering between the stars. These population studies require access to observational databases spanning multiple institutions and countries, demanding levels of international cooperation that exceed normal academic collaboration. The statistical frameworks being developed acknowledge that understanding 3I Atlas might require fundamentally rethinking our assumptions about the diversity and characteristics of interstellar visitors. The software development efforts represent another dimension of institutional investment that extends well beyond studying this single object. Programming teams at major observatories have been tasked with creating specialized analysis tools and algorithms designed specifically for processing 3I Atlas's unusual data signatures. These custom-built analytical frameworks will likely prove valuable for investigating future objects that challenge conventional classification schemes. The archive preservation efforts surrounding 3I Atlas research represent an unprecedented attempt to maintain complete records not only of observational data, but of the entire intellectual development process used to analyze this object. Future researchers studying similar phenomena will need access to the theoretical models, experimental techniques, and interpretive frameworks that emerge from the current investigation, acknowledging that understanding might require decades of sustained analysis. The personnel assignments and career redirections occurring in connection with 3I Atlas research reveal human dimensions of the institutional response that typically remain invisible to public view. Senior researchers are dedicating substantial portions of their professional focus to this single object, while junior scientists find their thesis projects and career development opportunities suddenly revolving around questions related to unusual interstellar visitors. These career investments represent long-term institutional commitments that extend well beyond the immediate observational window provided by 3I Atlas's passage through our solar system. They suggest recognition that understanding this object might define entire research programs and influence the direction of astronomical investigation for years to come. The philosophical discussions occurring within the scientific community provide perhaps the most revealing insights into how 3I Atlas is being perceived by those closest to the research. Private conversations between senior astronomers explore fundamental questions about the nature of scientific evidence, the boundaries of natural phenomena, and appropriate responses to observations that resist conventional explanation. These discussions acknowledge that 3I Atlas exists at the intersection of rigorous empirical science and genuine mystery, where careful observation encounters phenomena that stretch the explanatory power of established theoretical frameworks. The tone reflects both excitement about potential discovery and concern about maintaining scientific credibility when dealing with observations that challenge fundamental assumptions. The technology development programs inspired by 3I Atlas investigations represent investments in capabilities that will benefit astronomical research for decades to come. New spectroscopic techniques, enhanced data analysis algorithms, and improved theoretical modeling capabilities developed for this object will advance our ability to study other unusual phenomena that push the boundaries of current observational and analytical capabilities. The interdisciplinary networks emerging from 3I Atlas research connect astronomers with experts from fields rarely involved in astronomical investigation, creating collaborative frameworks that transcend traditional academic boundaries. Understanding this object requires expertise in atmospheric chemistry, materials science, information theory, and computational modeling, working together in unprecedented coordination. As 3I Atlas continues its approach toward the October perihelion encounter that represents our final opportunity for detailed observation, the gap between public communications and institutional activities continues to reveal the extraordinary nature of this cosmic visitor. The careful diplomatic language of official statements contrasts sharply with the urgent mobilization of resources and intellectual effort occurring behind the scenes. The pattern emerging from this institutional response suggests recognition that 3I Atlas represents something requiring the complete attention of the global scientific community, even if that recognition remains largely hidden from public view. Whether the ultimate discoveries justify this unprecedented mobilization of resources and expertise, the investigation itself has already transformed how astronomy approaches objects that challenge our understanding of what's possible in the universe. The countdown toward perihelion creates an atmosphere of controlled urgency within observatories worldwide, where decades of training in measured scientific discourse encounters the reality that something genuinely unprecedented may be unfolding in our cosmic neighborhood. The institutional machinery of modern astronomy finds itself operating in uncharted territory, where standard protocols prove inadequate for the scale of mystery this interstellar visitor presents. In the quiet spaces between official statements and private communications, between data collection and confident interpretation, we find ourselves witnesses to a moment that may represent a fundamental transition in our relationship with the cosmos. The careful silence surrounding 3I Atlas's most intriguing properties speaks not of conspiracy or concealment, but of institutional recognition that some discoveries require extraordinary caution, precisely because their implications might extend far beyond the boundaries of conventional astronomical investigation. The cosmic visitor continues its ancient journey according to the inexorable mathematics of orbital mechanics, indifferent to human schedules and institutional concerns, carrying within its chemical signatures and hidden structure the potential answers to questions that challenge everything we thought we understood about visitors from the stars. In the careful language of scientific papers and the measured restraint of official communications, we can read the outlines of a discovery that may forever change our understanding of what's possible in the vast laboratory of interstellar space. The gravitational mathematics that govern 3I Atlas's trajectory tell their own story about timing that seems almost too convenient to be coincidental. When you calculate backwards through the object's hyperbolic path, tracing its journey from the depths of interstellar space into our solar system, something remarkable emerges from the orbital mechanics. This visitor didn't simply stumble into our cosmic neighborhood through random gravitational influences. Its approach vector and velocity profile suggest a path that maximizes observational opportunities while minimizing the time available for detailed study. Consider the geometric precision of what we're witnessing. 3I Atlas arrived from the direction of the constellation Sagittarius, approaching our solar system at an angle that brings it remarkably close to multiple planetary targets during its brief passage. The object will sweep past Mars at a distance that positions European Space Agency orbiters for unprecedented close-range observations, continue toward a perihelion encounter that places it at the optimal distance for maximum solar heating without complete destruction, and then begin its departure along a trajectory that provides final observational opportunities from Earth-based telescopes. The statistical analysis of this pathway reveals probabilities that strain credibility when attributed to pure chance. Independent calculations by multiple research teams converge on figures suggesting less than a 5,000th of 1% likelihood that such a trajectory would occur naturally through random gravitational interactions. These aren't rough estimates or preliminary calculations. These are precise mathematical analyses conducted by institutions with decades of experience in orbital mechanics and celestial navigation. Yet what makes these probability calculations even more intriguing is how they interact with the timeline of human technological development. 3 Atlas's arrival coincides almost perfectly with our species' emergence as a civilization capable of detecting and analyzing interstellar visitors through sophisticated spectroscopic techniques. A few decades earlier, we would have lacked the instruments necessary to recognize its unusual chemical signatures. A few decades later, we might possess technologies that would make its camouflage ineffective. The window of technological capability that allows us to observe 3I Atlas while remaining uncertain about its ultimate nature seems remarkably narrow from a cosmic perspective. This temporal precision adds another layer of apparent intentionality to what could otherwise be dismissed as cosmic coincidence, suggesting either extraordinary luck or systematic planning that operates on timescales extending across multiple human generations. The deep field observations conducted by multiple observatories reveal background context that makes 3I Atlas even more anomalous when compared to other interstellar objects. Survey programs that scan vast regions of space for incoming visitors typically detect objects months or years before they reach the inner solar system, providing extended opportunities for preliminary study and observation planning. 3I Atlas appeared with relatively little advance warning, as if it had been deliberately concealed during its approach until optimal observation conditions were achieved. The stealth characteristics become even more apparent when you examine how the object managed to avoid detection by automated sky surveys that routinely catalogue millions of moving objects each night. The algorithms designed to identify asteroids and comets are specifically programmed to flag objects with the motion characteristics displayed by 3I Atlas. Yet this visitor remained invisible to our most sophisticated detection systems until its chemical activity made concealment impossible. The thermal signature analysis conducted by infrared telescopes reveals another dimension of the mystery that official communications carefully avoid discussing in detail. Objects traveling through interstellar space for millions of years should display temperature characteristics that reflect their long exposure to cosmic background radiation and their thermal history during the journey between stellar systems. 3I Atlas exhibits thermal properties that don't match theoretical predictions for ancient interstellar wanderers. The temperature distribution across its surface, as measured through infrared spectroscopy, shows patterns that seem almost too uniform for a natural object that should have experienced random heating and cooling cycles during its cosmic journey. Natural comets typically develop thermal gradients and surface variations that reflect their chaotic rotational states and irregular compositions. The thermal homogeneity observed in 3I Atlas suggests either formation under extraordinarily controlled conditions or active temperature regulation that maintains optimal conditions for its chemical processes. The magnetic field measurements present yet another puzzle that challenges natural explanations for this visitor's properties. Interstellar objects should carry magnetic signatures that reflect their formation environments and their interactions with cosmic magnetic fields during their lengthy journeys through space. 3I Atlas displays magnetic characteristics that don't match expectations for objects that formed around other stars and traveled through the magnetized plasma of interstellar space. The magnetic field strength and orientation patterns suggest either a composition that includes materials not typically found in natural comets or active magnetic field generation that requires internal energy sources beyond what should exist in a frozen nucleus. These magnetic anomalies provide another independent line of evidence that 3I Atlas operates according to principles that stretch physics. The gravit-conventional understanding of interstellar objectational effects that 3I Atlas exerts on nearby space debris and dust particles reveal mass distribution characteristics that don't align with expectations for natural comet nuclei. Precision tracking of particles in the object's vicinity suggests a density profile that's more organized than the random distribution of ice and rock that should characterize objects formed through natural accretion processes in protoplanetary disks. The gravitational mapping implies internal structure with geometric regularity that would be extraordinary in natural objects, but might be expected in artificially constructed systems. These measurements operate at the very limits of current gravitational detection capabilities, requiring analysis techniques that push our understanding of how to extract structural information from subtle gravitational influences. The seismic analysis conducted through radio telescopes attempting to detect internal vibrations reveals another layer of structural information that complicates natural explanations for 3I Atlas. Natural comet nuclei should display characteristic vibration patterns when subjected to thermal stress, as solar heating causes differential expansion and contraction of different materials within the nucleus. 3I Atlas exhibits seismic signatures that suggest internal damping mechanisms that suppress the random vibrations typical of natural objects undergoing thermal cycling. The vibration patterns appear structured and controlled rather than chaotic, as if internal systems were actively managing mechanical stress to maintain optimal operating conditions for whatever processes drive its unusual chemical emissions. The particle release analysis reveals systematic patterns in how 3I Atlas ejects material into its surrounding coma that don't match the random outgassing typical of natural sublimation processes. High-resolution imaging shows dust and gas being released in geometric patterns that maintain remarkable consistency across different observational epochs, suggesting either impossible natural organization or active control over material ejection processes. The velocity profiles of ejected particles display distributions that seem optimized for maximum coma density while minimizing the energy required for material release. This optimization appears to serve no obvious natural function, but would be valuable for maintaining camouflage if the object were designed to appear as a conventional comet, while concealing its true nature beneath layers of carefully controlled emissions. The chemical pathway analysis conducted by atmospheric modelers reveals reaction networks within 3I Atlas's coma that operate with efficiency levels rarely seen in natural chemical systems. The conversion of precursor molecules into the observed spectroscopic signatures follows pathways that seem almost engineered for maximum information content, while maintaining plausible natural explanations for individual chemical processes. The molecular formation rates and destruction mechanisms create chemical equilibria that persist across changing solar distances and thermal conditions in ways that suggest active regulation rather than passive response to environmental changes. These chemical control systems would require sophisticated mechanisms that don't exist in known natural processes, but might be expected in technological systems designed to maintain specific chemical signatures under varying external conditions. The isotopic fingerprinting efforts have produced preliminary results that challenge assumptions about 3I Atlas's formation environment and evolutionary history. The ratios of different isotopes detected in its emissions don't match patterns typical of objects formed in stellar environments similar to our solar system, but they also don't conform to expectations for objects that experience standard interstellar processing during extended cosmic journeys. The isotopic signatures suggest either formation under conditions that don't exist in known astrophysical environments, or artificial isotopic manipulation that could only be achieved through technological processes. These measurements require confirmation through multiple independent analyses, but they provide another line of evidence that 3I Atlas doesn't fit conventional categories for natural cosmic objects. The electromagnetic emission analysis reveals subtle patterns in the radio and microwave radiation emitted by 3I Atlas that don't match the random electromagnetic noise expected from natural plasma processes in comet comas. The emission patterns display what signal processing experts describe as information theoretic structure that could indicate either unknown natural phenomena or extremely sophisticated communication systems disguised as natural processes. The electromagnetic signatures are subtle enough that they could plausibly be attributed to natural plasma physics, yet organized enough that they might contain encoded information if analyzed using appropriate decoding techniques. This ambiguity seems almost deliberately crafted to maintain uncertainty about whether we're observing natural phenomena or artificial signals camouflaged to appear natural. The trajectory modification capabilities implied by the small but systematic deviations from purely gravitational motion suggest that 3I Atlas possesses some form of active propulsion or attitude control system. The magnitude and timing of these trajectory adjustments are consistent with gas release from natural outgassing, but the precision and coordination of the changes suggest systematic control rather than random volatile release. The propulsion signatures are subtle enough to maintain plausible deniability as natural phenomena, while providing sufficient maneuvering capability to maintain optimal observation geometries throughout the object's passage through our solar system. This level of precision in apparent natural processes pushes the boundaries of what could be achieved through coincidence alone. The energy balance calculations for 3I Atlas reveal thermal management that seems almost too efficient for natural processes operating in the extreme conditions of near-solar space. The object maintains remarkably stable internal temperatures despite the dramatic changes in solar heating that should create significant thermal stress and irregular heating patterns. The energy distribution within the nucleus appears optimized for maintaining the chemical processes that produce its unusual spectroscopic signatures, while minimizing the thermal effects that would be expected to disrupt delicate molecular formation pathways. This thermal control suggests either natural processes that operate with impossible efficiency or artificial thermal management systems designed to maintain optimal conditions for whatever functions 3I Atlas is designed to perform. The structural integrity analysis, based on how the object responds to gravitational stresses during its close approach to the Sun, reveals mechanical properties that don't match expectations for natural comet nuclei, composed of loosely consolidated ice and rock. The object maintains structural coherence under conditions that should cause significant deformation or fragmentation in natural objects with similar apparent density and composition. The mechanical strength characteristics suggest either materials with properties not found in natural solar system objects or internal structural reinforcement that provides artificial structural support. These engineering requirements would be unnecessary for natural objects, but might be essential for technological systems designed to maintain functionality while masquerading as natural comets during close solar encounters. The communication analysis, conducted by intelligence agencies working in coordination with astronomical institutions, has identified subtle patterns in 3I Atlas's behavior that could represent information exchange with external systems beyond our current detection capabilities. The patterns appear in the timing of chemical releases, the orientation changes during rotation, and the subtle trajectory modifications that collectively could serve as a sophisticated communication protocol. These potential communication signatures are embedded within apparently natural processes in ways that would be invisible to conventional astronomical analysis, but might be detectable using code-breaking techniques developed for analyzing structured information hidden within seemingly random data streams. The involvement of cryptographic experts in astronomical analysis represents an unprecedented intersection between traditional astrophysics and intelligence analysis. The systems integration analysis reveals that all of 3I Atlas's anomalous characteristics work together in coordinated fashion that would be extraordinary in natural objects, but might be expected in designed systems where different subsystems serve complementary functions. The chemical emissions provide camouflage. The thermal management maintains optimal operating conditions. The trajectory control ensures proper positioning, and the structural integrity enables survival in extreme environments. This level of systems coordination suggests either impossible natural organization or sophisticated engineering that integrates multiple technological subsystems into a coherent platform designed to accomplish specific objectives while maintaining the appearance of a natural interstellar comet. The technical complexity implied by such integration would represent engineering capabilities far beyond current human technology. The temporal correlation analysis reveals that 3I Atlas's various anomalous behaviors are synchronized in ways that suggest centralized control rather than independent natural processes, operating according to separate physical mechanisms. The timing of chemical releases correlates with orientation changes, which correlate with trajectory adjustments, which correlate with thermal variations in patterns that seem almost algorithmic in their precision. This temporal coordination implies information processing capabilities that could enable the object to monitor its environment, assess observational conditions, and adjust its behavior to maintain optimal performance while preserving the appearance of natural comet activity. Such adaptive behavior would require computational systems that don't exist in natural objects, but might be essential components of sophisticated reconnaissance platforms. The pattern recognition analysis conducted using artificial intelligence systems trained specifically to identify structured behavior in complex datasets has detected what machine learning experts describe as systematic signatures embedded within 3I atlas's apparently random variations in brightness, chemical emissions, and positional changes over time. These AI-detected patterns are subtle enough to escape human pattern recognition, but organized enough to suggest underlying systematic processes that generate apparently natural behavior through controlled mechanisms. The patterns don't definitively indicate artificial origin, but they provide statistical evidence for organization levels that would be extremely unlikely in purely natural systems. The comparative analysis with other interstellar objects reveals that 3I Atlas exhibits combinations of characteristics that have never been observed in natural comets from either our solar system or other stellar systems. While individual, anomalous properties might be explainable through exotic but natural processes, the complete suite of unusual characteristics collectively challenges the probability limits of natural occurrence. The statistical framework developed for evaluating the cumulative probability of all observed anomalies suggests that the likelihood of 3I Atlas representing a natural object with coincidentally unusual properties across multiple independent measurement categories approaches mathematical impossibility. These calculations don't prove artificial origin, but they establish probability thresholds that natural explanations must overcome. The observational bias analysis acknowledges that human psychological tendencies to see patterns where none exist could contribute to the perception of artificial characteristics in what might be purely natural phenomena. However, the systematic nature of the anomalies detected by multiple independent research teams using different instruments and analysis techniques suggests that observer bias alone cannot account for the consistency of unusual findings. The multimodal conformation of anomalous characteristics across electromagnetic, gravitational, chemical, thermal, and structural measurement categories provides redundant verification that reduces the likelihood of systematic errors or psychological bias creating false impressions of artificial organization in natural processes. The technological capability assessment explores what level of engineering sophistication would be required to create an artificial object with 3I Atlas's observed characteristics, and concludes that such construction would require scientific understanding and manufacturing capabilities far exceeding current human technology. The precision of chemical control, thermal management, and structural integration implies technological development that might require centuries or millennia beyond our current capabilities. This technological assessment doesn't determine whether 3I Atlas is artificial, but it establishes that if the object were artificially constructed, its creators would possess scientific and engineering capabilities that place them far beyond human technological development. Such advanced capabilities would enable construction of reconnaissance systems that could study emerging civilizations while maintaining perfect camouflage as natural phenomena. The strategic analysis conducted by defense and intelligence experts examines what objectives might motivate advanced civilizations to deploy sophisticated reconnaissance platforms disguised as natural interstellar comets, and concludes that such systems would provide ideal platforms for studying developing civilizations without triggering defensive responses or cultural disruption. The strategic advantages of comet-camouflaged reconnaissance include extended observation periods, close approach opportunities, chemical and physical analysis capabilities, and departure trajectories that prevent interception or detailed study by the observed civilization. These operational characteristics would make comet-disguised platforms optimal for gathering intelligence about emerging technological civilizations while maintaining strategic ambiguity about their artificial nature. The philosophical implications of 3I Atlas extend beyond questions of natural versus artificial origin into fundamental considerations about humanity's readiness for contact with advanced civilizations and our psychological preparation for discovering that we exist under observation by intelligences with capabilities that exceed our understanding. The carefully maintained ambiguity surrounding 3I Atlas's true nature might itself represent sophisticated psychological preparation, allowing human civilization to gradually adjust to possibilities that might otherwise prove culturally disruptive if revealed through unambiguous artificial signals or obvious technological demonstrations. The policy implications of potential artificial origin for 3I Atlas have generated classified discussions within government agencies about appropriate responses to scenarios involving advanced surveillance by non-human intelligences. These policy frameworks explore diplomatic, scientific, and security considerations that would apply if astronomical observations were to provide definitive evidence of artificial origin for interstellar visitors. The institutional preparations acknowledge that discovery of advanced extraterrestrial technology would require coordinated international responses extending well beyond traditional scientific investigation into diplomatic, security, and cultural domains that have no precedent in human experience. The policy frameworks being developed operate in hypothetical contexts, but establish procedural foundations for scenarios that may prove essential if 3I Atlas or similar objects provide unambiguous evidence of non-human intelligence. As 3I Atlas continues its precisely calculated journey toward the October encounter that will provide our final opportunities for detailed observation, the gap between what we observe and what we can definitively conclude continues to widen. The accumulating evidence for systematic, coordinated, and apparently purposeful behavior challenges natural explanations while falling just short of providing unambiguous proof of artificial origin. The cosmic visitor maintains its diplomatic silence, revealing just enough unusual characteristics to challenge our assumptions, while preserving sufficient ambiguity to maintain plausible natural explanations for each individual anomaly. This careful balance between revelation and concealment might itself represent the most sophisticated aspect of whatever intelligence guides this mysterious object through our cosmic neighborhood. In the quiet hours between observation and understanding, between data collection and confident interpretation, we find ourselves confronted with possibilities that stretch our scientific vocabulary to its limits, while challenging our most fundamental assumptions about intelligence, technology, and our place in a universe that may be far more populated and far more carefully monitored than we ever dared imagine. The bureaucratic machinery of modern astronomy operates according to established rhythms that have served the scientific community for decades. Peer review cycles that typically span months, funding decisions that unfold over years, and publication schedules that accommodate the leisurely pace of cosmic phenomena. Yet 3I Atlas has shattered these comfortable timelines, forcing institutions designed for methodical investigation to operate at speeds that would have been unimaginable just months ago. Picture the controlled chaos unfolding behind the scenes at major observatories worldwide. Research proposals that would normally require committee approval and months of scheduling are being fast-tracked through emergency procedures that bypass standard protocols. Graduate students find their carefully planned dissertation projects suddenly abandoned in favor of 3I Atlas research that promises career-defining discoveries but offers no guarantee of conventional academic outcomes. The funding streams tell their own story about institutional priorities that exist far from public view. Emergency research grants are being approved at rates that exceed normal annual budgets, with review processes compressed from months into weeks. When academic institutions begin redistributing resources on such scales, they're making statements about scientific significance that their public communications carefully avoid acknowledging directly. The computing resources being redirected toward 3I Atlas analysis represent perhaps the most visible indicator of institutional urgency. Supercomputing facilities that normally allocate processing time through competitive applications spanning multiple funding cycles have dedicated substantial computational capacity to modeling this single object's behavior. The algorithms being developed specifically for analyzing its unusual properties require processing power that exceeds what most astronomical projects receive over their entire operational lifetimes. Consider the human resources being quietly reassigned to 3I Atlas research across institutions worldwide. Senior faculty members are postponing sabbaticals, redirecting their research programs, and cancelling conference presentations to focus exclusively on this interstellar visitor. These aren't casual academic interests or opportunistic research pivots. They represent fundamental reorientations of professional priorities by researchers who recognize something extraordinary unfolding in real time. The technical challenges facing instrument teams push current technology beyond its designed operational parameters. Spectrographs optimized for studying distant galaxies are being recalibrated for extracting maximum information from a rapidly moving target that presents observational challenges unlike anything in their technical specifications. The precision required for detecting those subtle chemical signatures demands integration times and signal processing techniques that strain the capabilities of even our most advanced facilities. The international coordination networks operating behind the scenes reveal cooperation levels that transcend normal academic collaboration. Private communication channels between observatory directors discuss scheduling conflicts, data sharing protocols, and resource allocation, with an urgency typically reserved for responding to cosmic catastrophes like supernovae or gamma-ray bursts. Yet 3I Atlas isn't a transient explosion demanding immediate response. It's a slowly evolving mystery that somehow commands the same institutional attention as the most dramatic events in the universe. The data quality standards being applied to 3I Atlas observations exceed requirements for typical astronomical research by factors that reflect the extraordinary nature of what researchers believe they might be documenting. Multiple independent confirmations are being demanded for findings that would normally be accepted based on single instrument observations. Cross-calibration between different facilities has become essential rather than optional, creating verification networks that operate in real time rather than through traditional publication cycles. The archive preservation efforts surrounding this investigation represent unprecedented attempts to maintain complete documentation of not just observational data, but the entire intellectual framework being developed to understand this object. Future researchers studying similar phenomena will need access to theoretical models, analysis techniques, and interpretive approaches that emerge from current work. Acknowledging that understanding might require decades of sustained investigation extending well beyond the brief observational window this visitor provides. The personnel security protocols being implemented at some facilities suggest institutional recognition that 3I Atlas research might involve discoveries requiring careful handling of sensitive information. While such measures aren't unprecedented in astronomy, their application to studying what appears to be a natural comet indicates concerns about potential findings that could prove culturally or politically significant beyond normal scientific discoveries. The media relations strategies being developed reflect lessons learned from previous encounters with unusual astronomical objects, particularly the intense speculation that surrounded Oumuamua's anomalous characteristics. Institutional communications emphasize ongoing investigation while carefully avoiding language that might encourage premature conclusions about phenomena that remain scientifically uncertain. The challenge lies in acknowledging genuine mystery without fueling speculation that could later prove embarrassing if natural explanations emerge. The software development efforts represent investments in analytical capabilities that extend far beyond studying this single object. Custom algorithms for processing unusual spectroscopic signatures, specialized modeling tools for carbon dioxide-dominated comas, and statistical frameworks for evaluating anomalous observations are being developed with sophistication levels that suggest preparation for analyzing similar phenomena that might appear in future observations. The theoretical physics community faces unprecedented challenges in developing explanations for 3I Atlas that remain consistent with established science while accounting for its complete range of unusual properties. The most sophisticated models acknowledge fundamental limitations in their explanatory power, able to address individual characteristics while struggling to provide comprehensive frameworks that encompass all observed anomalies simultaneously. The laboratory experiments being conducted in parallel with astronomical observations represent attempts to bridge the gap between theoretical predictions and actual measurements. Research teams are testing whether known chemical processes can account for the selective metal release and unusual molecular signatures observed spectroscopically, working at the intersection of atmospheric chemistry, materials science, and astrophysics under conditions that push terrestrial experimental capabilities to their limits. The educational implications of 3I Atlas research are already transforming how astronomy programs approach instruction in observational techniques and data analysis. Graduate students are receiving specialized training in spectroscopic methods and chemical modeling that were developed specifically for this investigation, creating educational programs that acknowledge the need for expertise in analyzing phenomena that challenge conventional theoretical frameworks. The technology transfer programs emerging from 3I Atlas research are producing innovations with applications extending well beyond astronomy. Pattern recognition algorithms developed for identifying subtle signals in complex datasets, thermal modeling techniques adapted for unusual material compositions, and statistical methods for evaluating low-probability events are finding applications in fields ranging from climate science to materials engineering. The philosophical discussions occurring within the scientific community reveal how 3I Atlas is forcing researchers to confront fundamental questions about the nature of evidence, the boundaries of natural phenomena, and appropriate responses to observations that resist conventional explanation. These conversations acknowledge that the object exists at the intersection of rigorous empirical science and genuine mystery, where careful observation encounters phenomena that stretch the explanatory power of current understanding. The interdisciplinary collaboration networks emerging from this research connect astronomers with experts from fields rarely involved in astronomical investigation. Understanding 3I Atlas requires expertise in atmospheric chemistry, materials, science, information theory, and computational modeling, working together in ways that transcend traditional academic boundaries and create new models for how complex scientific investigations might be conducted. The public engagement strategies being developed acknowledge that 3I Atlas exists at the intersection of legitimate scientific mystery and popular fascination with possibilities that extend beyond conventional astronomy. Science communicators are working to convey genuine intrigue while maintaining appropriate distinctions between established observations and speculative interpretations, using public interest to promote broader scientific literacy while managing expectations about how quickly complex mysteries can be resolved. The historical precedent analysis being conducted by science policy experts examines how the scientific community has previously handled discoveries that challenged established paradigms, seeking guidance for managing investigations that might produce findings with implications extending beyond traditional astronomical research. These studies acknowledge that certain discoveries require institutional responses that transcend normal academic procedures while maintaining scientific rigor and public trust. The risk assessment protocols being developed explore potential consequences of various discovery scenarios, from confirmation of exotic but natural phenomena to possibilities that might require responses extending beyond traditional scientific investigation. These planning exercises operate in hypothetical frameworks, but establish procedural foundations that could prove essential if observations produce findings with broader cultural or policy implications. The quality control mechanisms being implemented for 3I Atlas research exceed standards typically applied to astronomical investigations, reflecting institutional recognition that this object study might produce findings requiring extraordinary verification before public dissemination. Multiple independent research teams are analyzing identical datasets, cross-checking results, and validating conclusions through redundant analytical approaches that minimize possibilities for systematic errors or misinterpretation. The institutional memory preservation efforts ensure that the complete intellectual development process surrounding 3I Atlas research will remain available for future investigators. The approaches being developed for studying this object, the theoretical frameworks being constructed, and the analytical techniques being refined represent intellectual infrastructure that could prove valuable for investigating other unusual phenomena that challenge conventional understanding. The career development programs being established acknowledge that 3I Atlas research is creating expertise in areas that didn't exist within traditional astronomical curricula. Young researchers are developing specializations in spectroscopic analysis of unusual objects, theoretical modeling of exotic chemical processes, and statistical evaluation of anomalous phenomena that position them to lead future investigations of similar mysteries. The international cooperation frameworks being established for 3I Atlas observations provide models for how the global scientific community might respond to future discoveries requiring rapid, coordinated investigation. The communication networks, data sharing protocols, and resource allocation procedures developed for this object create institutional infrastructure that could prove valuable for studying other phenomena, demanding immediate attention from multiple facilities worldwide. The long-term monitoring programs being established acknowledge that understanding 3I Atlas might require observations extending beyond its current passage through our solar system. Tracking networks are being developed to maintain surveillance of the object as it recedes toward interstellar space, providing data about its post-perihelion evolution that could resolve lingering questions about its fundamental nature and behavior patterns. The archival research programs are systematically examining decades of astronomical survey data, searching for any previous observations of 3I Atlas that might have been missed or misclassified during its long approach toward our solar system. These digital archaeology projects require massive computational resources, but could provide crucial information about the object's behavior during phases of its journey that weren't subject to detailed contemporary analysis. The calibration verification efforts represent perhaps the most technically demanding aspect of ensuring that 3I Atlas observations meet the extraordinary standards required for studying phenomena that challenge established understanding. Every instrument involved in the investigation is undergoing calibration procedures that exceed normal operational requirements, with cross-verification between facilities that demands unprecedented precision in measurement standards and systematic error analysis. The theoretical development programs are establishing research frameworks that could prove essential for understanding not only 3I Atlas, but potentially similar objects that might appear in future observations. The conceptual tools being developed for analyzing unusual chemical signatures, anomalous physical properties, and unexpected behavioral patterns represent intellectual infrastructure that extends well beyond studying this single visitor. As 3I Atlas continues its precisely choreographed dance through our solar system, approaching the October encounters that will provide our final opportunities for detailed observation, the institutional response continues to evolve in ways that reflect the extraordinary nature of what we're witnessing. The careful balance between scientific rigor and institutional urgency, between public communication and private investigation, between established procedures and emergency protocols, reveals a scientific community operating at the boundaries of its normal capabilities. The cosmic visitor maintains its enigmatic performance, revealing just enough unusual characteristics to challenge our assumptions while preserving sufficient ambiguity to maintain uncertainty. Revelation and concealment represents the inevitable about its ultimate nature. Whether this careful balance between result of studying exotic natural phenomena at the limits of our capabilities or something more systematic and purposeful remains the central question that will define how we remember this remarkable encounter. In the quiet hours between observation sessions, between data processing runs, between theoretical calculations and experimental validations, we find ourselves participants in a story that stretches beyond traditional boundaries of astronomical investigation into territory where science encounters mystery, where careful empirical observation meets phenomena that resist comfortable categorization, and where the universe reminds us that our understanding of what's possible remains wonderfully, frustratingly incomplete. The methodical accumulation of evidence continues according to schedules determined by orbital mechanics rather than human curiosity, while institutional responses operate according to urgencies that transcend normal academic timelines. In this intersection of cosmic time and human investigation, 3I Atlas continues to write its story across our skies, carrying within its chemical signatures and behavioral patterns the potential answers to questions we're only beginning to learn how to formulate properly. The silence between what we observe and what we can confidently conclude grows more profound with each passing day, creating information landscapes where the most significant developments remain largely invisible to public view, while the most dramatic possibilities capture imagination and speculation. In this gap between institutional caution and popular curiosity, our interstellar visitor maintains its diplomatic ambiguity, neither confirming nor denying the extraordinary possibilities it represents, following the ancient rhythms of celestial mechanics while perhaps orchestrating the most sophisticated first contact scenario in human history. The final phase of 3 Atlas's passage through our solar system approaches with the inevitability of a cosmic clockwork mechanism that cares nothing for human schedules or institutional anxieties. As October 30th draws near, and our mysterious visitor prepares for its closest encounter with the Sun, the observational opportunities that have defined this investigation will begin their irreversible transformation from present reality to historical record. Think about the peculiar nature of what we're experiencing. For the first time in human history, we possess the technological sophistication to detect and analyze the chemical signatures of an interstellar visitor in real time. Yet we remain fundamentally constrained by the same orbital mechanics that governed astronomical observation in Galileo's era. Our instruments have evolved beyond anything previous generations could imagine, but we're still bound by the simple reality that objects in space move according to gravitational mathematics rather than scientific convenience. The perihelion encounter will mark the climactic moment of this cosmic drama, when 3I Atlas reaches its closest approach to our Sun at approximately 1.4 astronomical units. At this distance, solar heating should drive the object's chemical activity to maximum intensity, potentially revealing secrets about its composition and behavior that have remained hidden during its long approach through the outer solar system. Yet this moment of peak revelation occurs precisely when observational geometry makes detailed study increasingly challenging from Earth-based facilities. The cruel irony embedded in this timeline cannot be overstated. Just when 3I Atlas should be displaying its most dramatic chemical signatures, just when those puzzling nickel emissions might reach peak intensity, just when any hidden structural features might finally become apparent through enhanced outgassing, our ability to observe these phenomena directly will be severely compromised by the object's position relative to the Sun's overwhelming brightness. The October 3rd Mars encounter represents our best opportunity to circumvent some of these observational limitations through the fortuitous positioning of European Space Agency orbiters that will find themselves closer to 3I Atlas than any Earth-based telescope could ever achieve. These robotic observers, originally designed to study Martian weather patterns and geological features, suddenly become humanity's most valuable assets for understanding our interstellar visitor during this critical phase of its solar system passage. The technical challenges facing the Mars-based observation campaign push spacecraft instrumentation beyond its original design parameters. Instruments optimized for studying planetary surfaces must be reconfigured to track a rapidly moving target that presents observational challenges unlike anything in their operational specifications. The pointing accuracy required for maintaining lock on 3I Atlas during its flyby demands navigation precision that exceeds normal planetary observation protocols. Consider the human drama unfolding behind these technical preparations. Mission controllers who spent years learning to operate these spacecraft for Martian science suddenly find themselves responsible for humanity's closest encounter with a potentially extraordinary cosmic phenomenon. The weight of this responsibility transforms routine spacecraft operations into historical moments that could define how we understand our place in the universe. The data transmission protocols being implemented for the Mars observations reveal the extraordinary priority being assigned to this encounter. Normal scientific data from these orbiters typically awaits routine transmission windows that accommodate the leisurely pace of planetary research. The 3I Atlas observations will receive priority transmission status, typically reserved for emergency communications, ensuring that crucial data reaches Earth-based analysts with minimal delay. The ground-based preparation for receiving and processing this Mars data involves coordination between institutions that rarely work together on such compressed timelines. University research teams, government laboratories, and private contractors are establishing joint analysis protocols that bypass normal academic territoriality in favor of rapid collaborative interpretation of potentially unprecedented observations. The backup observation strategies being developed acknowledge that the Mars encounter, despite its unique advantages, cannot provide complete answers to the fundamental questions surrounding 3I Atlas. Multiple contingency plans are being prepared for different scenarios, from technical failures that might compromise the Mars observations to discovery of phenomena that require entirely new analytical approaches. The post-conjunction emergence in early December represents what may be our final extended opportunity to study 3I Atlas before it fades beyond the detection limits of current instrumentation. By this time, the object will be receding from the Sun and likely decreasing in activity, but it will once again be positioned for observation by the complete suite of Earth-based and space-based facilities that have been tracking its approach since July. This December observation window carries particular significance for understanding how 3I Atlas responds to decreasing solar heating after its perihelion encounter. If the unusual chemical signatures observed during its approach show predictable evolution as the comet cools, this temporal pattern could provide crucial clues about whether we're witnessing natural thermal processes or something more systematic in its behavior patterns. The data analysis frameworks being prepared for the post-perihelion observations acknowledge that interpreting 3I Atlas's cooling behavior will require theoretical models that don't currently exist in astronomical literature. Research teams are developing new analytical tools specifically for understanding how the object's unusual chemistry might evolve as it moves away from maximum solar heating, creating intellectual infrastructure that could prove valuable for studying similar phenomena in future observations. The long-term tracking programs being established represent institutional recognition that understanding 3I Atlas might require observations extending well beyond its current passage through the inner solar system. Monitoring networks are being developed to maintain surveillance of the object as it recedes toward the outer planetary regions and eventually returns to interstellar space, providing data about its evolution that could resolve lingering questions about its fundamental nature. The statistical analysis frameworks being developed for evaluating the complete 3I Atlas dataset acknowledge that definitive conclusions about this object's nature might require mathematical approaches that transcend traditional astronomical methodology. The combination of chemical anomalies, behavioral peculiarities, and temporal correlations presents analytical challenges that push the boundaries of how we distinguish between natural phenomena and possibilities that challenge conventional understanding. The peer review processes being established for 3I Atlas research operate according to accelerated timelines that reflect the unique nature of studying a transient phenomenon that offers no second chances for verification or replication. Multiple independent research teams are analyzing identical datasets through parallel review processes that provide redundant validation while maintaining the quality control standards essential for extraordinary claims. The theoretical modeling community faces the challenge of developing explanations that can account for the complete range of unusual properties observed in 3I Atlas while remaining consistent with established physics. The most sophisticated models acknowledge fundamental limitations in their explanatory power, able to address individual characteristics while struggling to provide comprehensive frameworks that encompass all anomalous observations simultaneously. The experimental validation efforts represent attempts to bridge the gap between theoretical predictions and actual measurements through laboratory studies that test whether known chemical and physical processes can account for the phenomena observed in this interstellar visitor. These experiments operate at the intersection of multiple scientific disciplines, pushing the boundaries of what can be studied under controlled terrestrial conditions. The computational modeling programs being developed specifically for 3I Atlas require processing capabilities that exceed what most astronomical projects receive over their entire operational lifetimes. Supercomputing facilities are dedicating substantial resources to simulating the complex interactions between chemistry, physics, and thermal evolution that might produce the unusual signatures observed in this object. The machine learning applications being trained on 3I Atlas data represent cutting-edge attempts to identify patterns and correlations that might be invisible to human analysis. Artificial intelligence systems are being programmed to search for subtle regularities in the object's behavior that could provide clues about underlying systematic processes that generate apparently natural phenomena through controlled mechanisms. The database integration efforts are creating comprehensive archives that combine observations from multiple wavelength ranges, different types of instruments, and various analysis techniques into unified datasets that enable investigation of correlations and relationships that might not be apparent when studying individual measurement categories in isolation. The international cooperation protocols being established for 3I Atlas research create frameworks that could serve as models for how the global scientific community might respond to future discoveries requiring rapid, coordinated investigation. The communication networks, resource sharing agreements, and joint analysis procedures developed for this object represent institutional innovations that transcend normal academic collaboration. The technology development programs inspired by 3I Atlas investigations are producing advances in spectroscopic analysis, thermal modeling, and pattern recognition that will benefit astronomical research for decades to come. The specialized techniques being developed for studying this object's unusual properties are creating intellectual and technical infrastructure that could prove essential for investigating other phenomena that challenge conventional understanding. The educational transformation occurring within astronomy programs reflects recognition that 3I Atlas research is creating expertise requirements that didn't exist within traditional curricula. Graduate students and postdoctoral researchers are receiving specialized training in analytical methods and theoretical approaches that position them to lead future investigations of unusual cosmic phenomena. The policy discussion frameworks being developed explore how scientific institutions should respond to discoveries that might have implications extending beyond traditional academic research. These conversations acknowledge that certain findings could require coordinated responses involving governmental agencies, international organizations, and public communication strategies that transcend normal scientific publication processes. The quality assurance protocols being implemented for 3I Atlas research exceed standards typically applied to astronomical investigations, reflecting institutional recognition that this object study might produce findings requiring extraordinary verification before broader dissemination. Multiple independent validation procedures are being applied to ensure that any significant conclusions rest on foundations solid enough to withstand intense scrutiny. The historical documentation efforts are creating comprehensive records not only of observational data, but of the complete intellectual development process used to analyze this object. Future researchers studying similar phenomena will have access to the theoretical evolution, methodological innovations, and interpretive frameworks that emerge from current work. Acknowledging that understanding might require sustained investigation, extending beyond the immediate observational window. The career development implications of 3I Atlas research are already influencing how young scientists plan their professional trajectories. The expertise being developed for studying this object creates new specializations that could define entire research programs and academic careers. representing long-term investments in capabilities that might prove essential for understanding similar discoveries. The risk management protocols being developed acknowledge that 3I Atlas research operates in territory where traditional scientific methodology encounters phenomena that resist comfortable categorization. Institutional frameworks are being established to maintain scientific rigor while remaining open to possibilities that might challenge fundamental assumptions about natural processes and cosmic phenomena. The public communication strategies being refined reflect lessons learned from previous encounters with unusual astronomical objects, particularly the challenges of conveying genuine scientific uncertainty while avoiding both excessive speculation and premature dismissal of extraordinary possibilities. The goal is to maintain public engagement and interest while preserving the intellectual integrity essential for rigorous scientific investigation. The legacy planning surrounding 3I Atlas research acknowledges that this object's significance might extend far beyond its brief passage through our solar system. The analytical techniques, theoretical frameworks, and institutional innovations developed for studying this visitor could influence how astronomy approaches unusual phenomena for generations, creating intellectual infrastructure that serves the broader scientific community. As 3I Atlas continues its ancient journey, according to the inexorable mathematics of orbital mechanics, indifferent to human schedules and institutional urgencies, it carries within its chemical signatures and behavioral patterns the potential answers to questions we're only beginning to formulate properly. The careful silence surrounding its most intriguing properties speaks not of conspiracy or institutional concealment, but of scientific recognition that some discoveries require extraordinary caution, precisely because their implications might extend beyond the comfortable boundaries of conventional astronomical investigation. The countdown toward perihelion creates an atmosphere where decades of training in measured scientific discourse encounters the reality that something genuinely unprecedented may be unfolding in our cosmic neighborhood. Whether this encounter ultimately provides natural explanations for exotic phenomena or opens doorways to possibilities that challenge our understanding of what occurs in the universe. The investigation itself has already transformed how we approach the study of visitors from the stars. In the quiet spaces between observation and interpretation, between data collection and confident understanding, we find ourselves witnesses to a moment that may represent a fundamental transition in our relationship with the cosmos. The methodical accumulation of evidence continues according to celestial schedules that care nothing for human curiosity, while institutional responses operate according to urgencies that transcend normal academic timelines. The story of 3I Atlas continues to unfold in real time, written in wavelengths of light that carry information across vast distances, encoded in chemical signatures that speak of processes and environments we're only beginning to learn how to read. Each observation adds another piece to this cosmic puzzle, while each unanswered question opens new pathways for discovery that may extend far beyond our current ability to imagine their implications. The cosmic visitor maintains its enigmatic performance, revealing just enough unusual characteristics to challenge our assumptions while preserving sufficient ambiguity to maintain uncertainty about its ultimate nature. Whether this careful balance between revelation and concealment represents the inevitable result of studying exotic natural phenomena at the limits of our capabilities, or something more systematic and purposeful, remains the central question that will define how we remember this remarkable encounter with the unknown. As we reach the end of our journey through the carefully constructed silence surrounding 3I Atlas, we find ourselves standing at the intersection of rigorous science and cosmic mystery, where diplomatic language masks extraordinary possibilities and institutional caution conceals unprecedented mobilization. Whether this interstellar wanderer ultimately proves to represent exotic natural phenomena or something that fundamentally challenges our understanding of what's possible in the universe, its passage through our solar system has already transformed how we approach the unknown. Sleep well tonight, knowing that somewhere in the darkness above, ancient secrets continue their dance through our cosmic neighborhood.